Good afternoon, good evening, and good morning to you all. Now we are going to start the second day of the 3-day international conference, MAST 2022. Today is a special day for Indian mathematics. This day is celebrated as National Mathematics Day across India every year. National Mathematics Day is marked to recognize and celebrate the works of Srinivasa Ramanujan. Srinivasa Ramanujan, the Indian mathematical genius, was born on this day in 1887. Former Prime Minister Manmohan Singh on February 26, 2012 declared December 22 as the National Mathematics Day to mark the Indian mathematician's birth anniversary. Ramanujan is also known as the man who knew infinity. Ramanujan, who didn't receive any formal education in mathematics, has made several important contributions to the field of mathematics. Ramanujan's journey to begin as a genius started when he sent a letter to Professor Hardy in which he mentioned about 120 mathematical theorems. He joined Trinity College a few months before World War One. In 1916, Ramanujan was awarded the Bachelor of Science degree. In 1917, he was elected to the London Mathematical Society. In 1918, he was elected a Fellow of Royal Society of his research on elliptic functions and the theory of numbers. The same year, in October, he became the first Indian to be elected as a Fellow of Trinity College, Cambridge. In 1919, he returned to India due to his poor health. And a year later, on April 26, 1920, we lost him at the age of only 32. So today, the whole day of this conference is dedicated to this generous, genius Indian mathematician Ramanujan. So without any further delay, let us start the technical session 1A. The parallel session 1B is running parallelly through another Google Meet link. So if anybody from technical session B is present here, is kindly requested to join through the other link. So for this session, we have our session chair, Dr. Devnath, Sumit Devnath from NIT Jamshedpur. So may I request Sumit to please take over the session and please chair this session. Sumit?
Thank you, sir. Uh, so in this session, first let me tell you one thing. All of you will be given 10 minutes for your presentation and 2 minutes for the question answer session. So the first presentation will be probably will be given by Vinod Prasad and entitled "Study of Locally Convex Algebra on the Duality Theory." So Dr. Vinod Prasad, are you here?
Yes, sir.
Okay, you please start. You may start.
May I start, sir?
Yes, yes, please.
Namaste to each, sir. Uh, and according to different times, I want to say good evening, good morning, and good afternoon to all of sir.
Okay,
I'm
could you
Vinod
please share your
Prasad.
screen?
Just Is it good, sir?
It is not properly visible. So how did you share? Like, have you shared the whole screen or only the screen?
And
I
is it
I
good
mean,
now?
entire screen or a window only?
Just it should be.
But I don't think it is in slide mode. So if you can make it in slide mode, so it will be better.
Now is it good?
At the same time, the whole page is not visible. So in Word, there is a form. Like just a minute. So through which you can make it slide mode.
Just I only share the files. I haven't made slides, sir. Is it visible? Is it good, sir? Now?
Yeah, it is visible. You may start. You may start. Okay.
Okay, sir.
Without
Good
delaying.
good evening to all, sir. And first of all, I'm very happy and I'm very grateful to IMBIC and Dr. Abhishek Adhikari. And this time also, I want to remember Srinivasan Ramanujan and also all sorts. And without taking more times, I want to read my papers. I'm Vinod Prasad, Assistant Professor, Thakuram Campus, Tirvan University, Nepal. And the title of our paper is a study of uh, a study of locally convex algebras on the duality theory. And the authors are Vinod Prasad, Abhishek Kumar, Dashrath Prasad Rai, and Department of Mathematics, TRM Campus, Birganj, Nepal, PRRD College, Virginia, Bihar University, and A College, Mahua Vaisali, Bihar University. And the abstract of the paper is this present paper deals with the study of locally convex algebras on the duality theory. Here we consider a property of equicontinuous subsets of the dual of epsilon tensor product E and F, where E and F are the locally convex algebras, which are the inductive limits of the families EI, F, and Fj, respectively, of locally convex algebras by the linear mapping Fi and Hj, respectively. It is proved in this paper that epsilon tensor product of E and F, denote this one, epsilon tensor product of E and F, and the keywords are dual space, locally convex algebras, continuous space, inductive tensor product, linear matrix. Introduction. The introduction is the present work is an attempt towards the generalization of work done by E.G. Ifroj 1 and Catho 3 and 4. In fact, the present area is the extension of work done by Halab JR2, Kumar et al. 5, Srivastav et al. 6, Srivastav et al. 7, Srivastav et al. 8, Srivastav et al. 9, and Srivastav et al. 10. In this paper, we have studied analytically on dual of locally convex algebra. Mathematical treatment of the problem. Proposition. Let E be a locally convex algebra which is the inductive limit of a family EI uh, of locally convex, not necessarily Hausdorff algebras by the family uh, Fi of linear mappings. Let F be a locally convex algebra which is the inductive limit of a family Fj of a locally convex, not necessarily Hausdorff algebra by the family Hj of linear mappings. Let T denote the finest locally convex topology on E tensor product F, for which the linear mapping Fi tensor product Hj from Ei tensor epsilon tensor product Ei Fj to tensor product E tensor product F are continuous, and let E tensor product F with such a topology T be denoted by topological tensor product E and F, then every equicontinuous subset M of epsilon tensor product E and F prime is also an equicontinuous subset of topological tensor product E and F prime. Proof: it is well known that an inductive limit of locally convex Hausdorff algebras need not be Hausdorff. We therefore divide the proof into parts. Case first: if all the locally convex algebras EI, Fj are Hausdorff algebras and their inductive limits E and F are also Hausdorff algebras, then the proof is trivial on the ground that the maps Fi tensor product Hj from Ei epsilon tensor product Ei and Fj to E epsilon tensor product E and F are continuous. Hence, the topology T is finer than epsilon, and consequently, epsilon equicontinuity of M implies its T continuity, T equicontinuity. Case second: let the algebra Ei and Fj be not necessarily Hausdorff. The neighborhood base in E is given by the sets of the form L union runs over I Fi of Vi, where for each I, Vi is a basic neighborhood in Ei. Let us note that that indicates the absolutely convex envelope. Similarly, a neighborhood base in F is given by the sets of the form L union runs over J Hj of Wj, where for each J, Wj is a basic neighborhood in Fj. A base of neighborhood in topological tensor product E and F is formed by the sets of the form L union runs over Ij, Fj tensor product Hj of Vi0 tensor product Wj0 of 0, where the polars Vi0 are taken in Ei prime and the polars Wj0 are taken in Fj prime. So now recalling that Ei dash tensor product Fj is subset of Ei epsilon tensor product Ei and Fj prime. The polars Vi and tensor product J0 of 0 are taken in epsilon tensor product Ei and Fj. Let us note that Fi, a tensor product Hj, denotes the tensor product of the linear mapping Fi and Hj. A base of neighborhood in epsilon tensor product Ei and F is formed by the sets of the form L union runs over I Fi of Vi0, a tensor product L union runs over J Hj of Wj of 0 of 0, where the polar L union runs over I Fi of Vi0 is taken in E prime, and L union runs over J Hj of Wj of 0 is taken in F prime. And recalling that E prime tensor product F is subset of epsilon tensor product E and F prime. The final polar is taken in F and epsilon tensor product E and F. Now let M be an equicontinuous subset of E epsilon tensor product E and F prime. Then M is subset of L union runs over I Fi Vi of 0 tensor product L union runs over J Hj of Wj of 0 of 0 for some choice of Vij and Wij. So we shall prove that for each such choice of Vj and Wj, M is subset of L union runs over I and J Fi tensor product Hj of Vi0 tensor product W of 0 of 0 of 0, which will imply that M is an equicontinuous subset of topological tensor product E and F prime. It is sufficient to prove that L union runs over I Fi of Vi0, a tensor product L union j runs over j hj of wj of 0 of 0, which subset of L union runs over I and j fi tensor product hj of vi0 tensor product wf0 of 0 of 0. So now applying the theorem of bipolars, that it is sufficient to prove L of L union runs over I fi vi of 0 tensor product L union hj of wj of 0. It's subset of L union I runs over ij fi of tensor product hj of vi0 tensor product wj0 of 0, where the line segment above L is used to denote the closure. So now, since the right hand set in in subset in 4 is weakly closed and absolutely convex, it is sufficient to prove that L union runs over I if I of vi0 is tensor product L union runs over j of hj of wj of 0 is subset of L union runs over I and j if I tensor product hj of vi0 tensor product wj0 of 0. Now, if I dash and prime and hj prime denote respectively the transposage of fi and hj, then we have L union runs over I if I of vi0 is subset of fi dash inverse of vi0. L union runs over j hj of wj of 0 is subset of hj prime hj prime inverse of wj 0. Therefore, we have L union runs over I if I of vi0 tensor product L union hj of wj0 is subset of fi prime inverse of vi tensor product hj prime inverse of wj of 0. Hence, for proving 5, it is sufficient to prove that if I in prime of inverse vi0 tensor product hj prime inverse of wj0 is subset of L union runs over I and j of fi tensor product hj of vi0 tensor product wj0 of 0. Now let z is equal to fi dash inverse of ai tensor product hj dash inverse of bj be any element of the left hand set of subset in 6, and ai belongs to vi and bj belongs to wj0. Any element of L union runs over I and j of fi tensor product hj of vi0 tensor product wf0 of 0 is of the form x is equal to summation runs over ij aij fi tensor product hj of xij, where summation runs over ij of modulus of aij is less than equal to 1 and aij equal to 0 except for finitely many I and j, and xij belongs to vi0 tensor product wj0 of 0. Then modulus of inner product z and x is equal to modulus of inner product of fi dash inverse of ai tensor product hj dash of inverse of bj and summation aij of fi tensor product hj of xij is equal to modulus of summation aij tensor product fi dash inverse of ai tensor product hj dash of inverse of bj and fi tensor product hj of xij is equal to summation aij tensor inner product ai tensor product bj and fi dash inverse tensor product hj dash inverse of dash fi tensor product hj of
Now, please conclude. Excuse me, please conclude.
okay
You are
okay
already running out of time. Please conclude.
and acknowledgement. The authors are, we are very thankful to Professor Dr. Sn Jha, ex-head Department of Mathematics of and Professor PK Saran, ex-head of and likewise BP Singh, ex-head Professor Pradeep Kumar, University Department, and Professor Amit Sharma, Department Head, and mathematics, Bihar University, and this much is the, and there are the references, sir. Here the references, easy fourth, and likewise we can see on the screen there are the, we uses the references. Okay, sir. Thank you.
So, okay, thank you. Is there any question from the audience? Okay. So I just have one question. Like, what does mean by that epsilon tensor product? Uh, uh, Dr. Binod, can you hear me? Okay. Once again, thanks to Dr. Binod. Now let's go for the next speaker. The next speaker is Surajit Viswas. Surajit Viswas, are you here?
Yes, yes, yes. Am I audible, sir?
Yes, yes. So
Yeah.
so in the right now, the Surajit Viswas is going to present the paper entitled "Some Large Sets Near in Idempotent and Its Cartesian Product." Surajit, you may please start.
Okay.
Pardon? No.
Yeah. Is the screen visible, sir?
Yes, it is. Please tell.
Okay. So, first of all, I would like to thank the organizers for giving me the opportunity to present this paper in this conference, virtual conference. So, the title of the talk, as already said by Sir, is some large sets near idempotent and its Cartesian product. So, large sets means here in a combinatorial sense. So, about me, my name is Surajit Biswas and I am a PhD scholar at Ramakrishna Mission Vidya Mandir, Belur Math. Okay, so let me start with some preliminaries. So with the notation S, we'll denote any semigroup. And SD by SD, we mean a semigroup with discrete topology. And beta by beta S, we mean the Stonecheck compactification of S. So it's the maximal compactification in a sense for a given semigroup. And given a set X, we write P suffix F of X for the set of all finite non-empty subsets of X. So, okay, so just with the introduction, the notion of central subset was first introduced by Furstenberg for the semigroup natural number with addition. And later, the notion was generalized by Bargelsen and Hindman. And why this class of central sets are important? Because it is combinatorially very rich class of sets because they satisfy central sets theorem. So what is central set theorem? So it is not possible here to describe, but it is a combinatorially rich structure, which says that there are certain sets which satisfy a combinatorially rich structure, and central sets as defined by Furstenberg and later generalized by Bargelsen and Hindman, they also satisfy this kind of combinatorially rich structure. And later, a localized notion of central set called central set near idempotent was introduced by Tutkavani and Vaid. And I mean, though it is not shown in non-commutative case, but in a commutative semigroup, central sets near idempotent is a class of localized sets around an idempotent, which are combinatorially rich. Why? Because they satisfy the central sets theorem near idempotent. So there is a version of central sets theorem near idempotent. So references are given here. So okay. So and in this article, what do we show? It is motivated with the work of Hindman and Strauss. They have characterized when the finite or infinite Cartesian product of sets is piecewise syntactic or central. So in this article, we provide the localized notion of the same. That is, we provide partial characterizations for piecewise syntactic sets near idempotent and similarly central sets near idempotent. So these two are the main results of this article. Okay, so let me begin with some notations and some technicality that we'll use later. The notion of central sets near idempotent is algebraically defined as
Surajit?
structure on S. Beta SD can naturally be identified with a collection of ultrafilters on S. So I have given the reference because it is not possible to describe all the technicalities here. So identification later on. And the semigroup structure on S induces a unique semigroup structure on beta SD, so that beta SD becomes right topological semigroup. What do we mean by right topological? That means the right action of S on beta SD is continuous and with S content in its topological center. That means the right action and left action by S on beta SD both are continuous. That means that S content in its topological center. Okay, so the semigroup structure is given by this formula, that is for PQ belongs to Stonchek compactification. We define P plus Q in this way. And from now onwards, for technical simplicity, whenever we consider Stonchek compactification of a semigroup S, we write simply beta S. We will omit the suffix D from beta SD. Okay, so the rest of the details, we refer the book Algebra on Stonchek compactification by Heinemann and Strauss. Okay, so these are the beginning of the technicalities. I mean, for T plus, we let T plus be a semi-topological semigroup. Throughout this article, we assume all our semi-topological semigroup to be Hausdorff. Note that the semi-topological structure on the semigroup T is the topology on T such that for each x belongs to T, the left translation map Lx and the right translation map Rx are continuous. We denote the collection of idempotents in T by Et. Of course, we'll consider only those semi-topological semigroup for which Et is non-empty. Moreover, for every x belongs to T, tau x denote the collection of all neighborhood of x, where the set U is called a neighborhood of x if x belongs to the interior of U in T. Okay, so these are so here this definition is actually given by Tutkavani and Vaid. So they consider the semi group E S star denote. So the first let me read out the definition. Let S be a subsemi group of a semi-topological semigroup T but not inside T. This is the collection of all ultrafilters, so that if we consider of that element inside T, E will be inside that closure. So that is the main. So basically, we are considering the near E ultrafilters in beta S. So this equivalence can be shown, easily, almost very straightforward. That E star can be rewritten in this form: the all ultrafilters in beta S, such that if you consider any neighborhood of E, then U intersection S will be in P. So now similarly, we can generalize all our results to a general class of semigroup, that is dense near E subsemigroup. So what is the definition? Definitely let S be a subsemigroup of a semi-topological semigroup T, and let E belongs to Et minus S. S is said to be near E subsemigroup of T if E belongs to the closure of S inside T. So it can also be shown that E star is compact subsemigroup of beta S when we assume S to be a near E subsemigroup of a semi-topological semigroup T, and any compact right topological semigroup has a smallest ideal that will be used in the next definition of central sets, which is the union of minimal left ideal of S and also the union of minimal right ideal of S. So the next definition is of central sets. This is also given by Tutkavani and Vaid. So let S be a near E subsemigroup of a semi-topological semigroup T. Let K E star be the smallest ideal of the semigroup E star. Let a subset of S. Then A is central if there is some idempotent P in K E star with a subset of A contained in P. Now, we consider some any topological space, and we say that an element x in S, we say that x has a countable local base in X if X has a countable neighborhood base un in X. If un is countable neighborhood base for X, then one can, we can inductively filter out the or inductive intersection. And with this inductive intersection, we'll get a countable local base, so that one is contained in another in a filtered way. That means Vn plus 1 will be contained in Vn for each n. So without loss of generality, we can assume that for any countable local base, we can assume un plus 1 contained in un, just for simplicity in the proof. So now we'll recall the definitions of piecewise synthetic set, and of course another notion of thick set. So first we'll read out the this is the definition that we introduce. So let S be a Neary subsemigroup of a semitopological semigroup T with addition, and let A subset of S, then A is thick near E if there exists a neighborhood of E such that for each finite partition or finite subset of U intersection S F, and if you consider another neighborhood V of E, then there exists some X such that F plus X contained in A. So that means, locally, what is a thick set? If you translate this, a thick set is if you consider a finite subset of U intersection S. If you translate that by an element, that will be contained in the set. And of course, the next definition is of piecewise synthetic set. That is also
Surajit, excuse me, Surajit. Could you please go to your result and please conclude that?
I'll take maximum 1 minute.
Yeah, sure.
Is that okay? Yeah.
Yeah, it's fine.
So the next definition, yeah. So the next definition is of piecewise synthetic set. So what is the definition? Let me just intuitively state that piecewise synthetic set is that if you translate that by set, and that will be essentially thick. So it is basically the definition, basically the technicality, some technicality is there, but this is the meaning of the definition. So this is the final characterization. So it says that if you consider a collection of semitopological semigroup Ti and collection of subsemigroup Si, and consider Ei subset of Si, let we consider product semitopological semigroup T with box topology. Similarly, the product of Si and product of Ei and product of Ei. And this is the assumption that we have to take, that let E have a countable local base in T. Then this is, of course, we have to also assume that this Ai subset of Si is not thick near Ei. This collection of indices has to be finite. Then A is piecewise synthetic near E if and only for each I belongs to I, Ai is piecewise synthetic near Ei. And with the same assumption, only will exclude that E have countable local base in T. The conclusion also holds for central sets. So with that, these are the reference, and with this, I will conclude my talk. Thanks.
So thank you, Surajit, for your presentation. Is there any question from the audience? So, okay, fine. And our next speaker is Masin Jabel Ateya. Are you here? Ateya, are you here? Okay. Then S. Samanto, are you here?
Yes, I am here.
So the next presentation will be given by S. Samanto. The title of the presentation is Note on Simple Topological Ternary Semigroups. Samanto, you may please start.
Okay. Is it visible?
Yes, it is visible. But I
Yeah.
think you have. Okay, okay. Right now it's fine. It's fine. Yeah.
Good morning, good afternoon, and good evening to all. First of all, I would like to convey my sincere thanks to Team INVIC and Chairperson. Special thanks goes to Professor Abhishek Adhikari for his continuous effort to continue this international conference every year and in this particular time frame. Myself, Mr. Sapan Samanto, Assistant Professor, Goenka College of Commerce and Business Administration. Title of my talk is Note on Simple Topological Ternary Semigroup. So first I introduce something and thereafter preliminaries and come back to main result and finally references. Saying about topological ternary semigroup, in today's day topological semigroup theory is rich and lot of works are going on, and this journey was started during 1920s, beginning of the 1920s. At the same time, ternary algebraic system was started its journey, and a particular type of semigroup theory is a simple ternary semigroup which was done by Sija in his paper. What we will try to do in this presentation is that we shall try to introduce topology here so that it will become a topological ternary semigroup. A particular topological ternary semigroup later on we will introduce as simple topological ternary semigroup. We shall try to give some example of it and try to prove some relevant result in this connection. So before starting with this journey, we need to know some literature relating to ternary system. First of all is this non-empty set with associative ternary composition is called ternary semigroup. It contains an identity if it satisfies the condition Ex equals to Exe equals to Xe equals to X for all X belongs to this. If the lateral condition is omitted, then this element E is called a biunital element. An element is called idempotent if it satisfies the condition AQ equals to A, and the set of all idempotent elements we denote by S. Ternary semigroup is in case of ternary semigroup, it is called left cancellative, right cancellative, lateral cancellative if they satisfy 1, 2, 3, and we call it is cancellative if it becomes left, right, and lateral cancellative. Now, definition of ternary group is that a ternary semigroup S is called ternary group if for ABC belongs to S. These equations have solution in S. Using this, we can show that also it has unique solution. An element in case of ternary semigroup theory is called invertible or it has an inverse. If for each A there exists B such that ABX equals to BX equals to X, BA equals to X, AB equals to X for all X belongs to S, and is an non-empty subset of a ternary semigroup is called left ideal, right, respectively right lateral or two-sidal ideal if they satisfy those conditions simultaneously, and it is called an ideal if at the same time it becomes a left ideal, right ideal, lateral ideal. Okay, so additional condition which differs from semigroup theory is that of lateral ideal. Now, a ternary semigroup is called simple ternary semigroup if it doesn't contain any proper ideal. A ternary semigroup which contains a zero is called zero simple ternary semigroup if S cube not equals to zero and zero is the only proper ideal of S. Similarly, we can define simple ternary subsemigroup as well. Now, here are some results. First one is that a ternary semigroup is called T simple means two-sided simple if and only if TTA and Tt equals to T for all A in P. Thereafter, the necessary sufficient condition for a ternary semigroup to be a simple is if this satisfies this condition, if it is called zero simple, if this satisfies the condition TAT union TTA TT equals to T for all A belongs to T minus 0. Here is a result, preliminary result, which will helpful to prove the result that any any idempotent element of a cancellative ternary semigroup is also a biunital element. The following conditions for a ternary semigroup are equivalent. S is regular and cancellative. Every element has inverse, or every element of S is invertible, and S is ternary group. Uh, this is a definition of a kernel. The intersection of all ideal of a ternary semigroup, if it exists as a non-empty, then we call it as a kernel. And so it is to be noted that kernel is the smallest ideal of a ternary semigroup if it exists. Now we are coming to the topological part. So a topological ternary semigroup is a ternary semigroup associated with a multiplication which is continuous. Note that here we are considering minimum property as the Hausdorff property, because without considering Hausdorff, we cannot get much more topological structure on it. A topological ternary semigroup is called paratopological ternary group if this ternary semigroup becomes a ternary group. And here are some results I am simply omitting. Now I'm coming back to my main portion. Now, simple topological ternary semigroup. What is the definition of simple topological ternary semigroup? A topological ternary semigroup is called simple topological ternary semigroup if it doesn't contain any proper ideal. If S contains a zero element, same condition satisfied, only it contains zero element, then it becomes a zero simple topological ternary semigroup. Here are some examples. This is a continuous type of character. If we consider set of all negative real numbers with multiplication of real numbers, and if we consider discrete topology, then we can say that R minus is becomes a simple topological ternary semigroup. Second one is a discrete type of character, set of all odd integers with usual addition of integers, and discrete topology if we insert here, then we can say it is also becomes a simple topological ternary semigroup. And with negative real numbers, if we include 0, then we can show that this becomes a zero simple topological ternary semigroup. The first important result towards this is that if S is if the kernel K, kernel means intersection of all ideal of a topological ternary semigroup is non-empty, then K is a two-sided simple topological ternary subsemigroup of S. Again, if S contains an identity element, then this two-sided becomes simply simple topological ternary subsemigroup of S. Now, some necessary sufficient condition: a topological ternary semigroup without 0 is right simple if and only if xys equals to S for all xy belongs to S. It is called left simple if this satisfies the condition Sxy equals to X for all xy belongs to this. Same type of results are true for zero simple, the left zero simple, right zero simple as well. Okay, so now we are coming to the theorem number 0.33, where it says that S is a zero simple topological ternary semigroup and E is a non-zero idempotent element of S such that E acts as a biunital element of S. Then ESE is a zero simple topological ternary subsemigroup of S. Now, as a corollary of the last result, we can say let S be a zero simple cancellative topological ternary semigroup and E is a non-zero idempotent element of S. Then ESE is a zero simple topological ternary subsemigroup of S. And second one is that S be a zero simple paratopological ternary group and E is a non-zero idempotent element of S. Then ESE is also zero simple topological ternary subsemigroup of S. Here is one necessary sufficient condition. It says that a necessary and sufficient condition for a topological ternary semigroup S with 0 to be left zero simple is that SSX equals to S for all x belongs to S minus 0. Okay, as a note, similarly, we can show that for a topological ternary semigroup S with 0 is a right zero simple if and only if XSS equals to S for all x belongs to S minus 0. Let S be a compact topological ternary semigroup and A be a simple topological ternary subsemigroup of S, then we can show that closure also becomes a simple topological ternary subsemigroup of S. It is to be noted that the above result is true for left as well as right simple topological ternary semigroup. Point 39, it says that if S be a compact topological ternary semigroup with an identity element, then each minimal ideal of S is a simple topological ternary subsemigroup of S. An application of the last result says that if we consider the collection of arbitrary family of topological ternary semigroup and A alpha be the subsets of S alpha such that if S alpha is compact for each alpha in lambda, then this product is a minimum ideal of this product S if and only if A alpha is a minimal ideal of S alpha for each alpha belongs to lambda, provided S contains an idempotent element. Let S be a compact right simple topological ternary semigroup with an idempotent element, then we can show that this translation map is homeomorphic. So final two results are that every left simple topological ternary subsemigroup.
Please conclude.
Yes, this is last one. Every left simple topological ternary subsemigroup of a topological ternary semigroup containing a maximal left simple topological ternary subsemigroup of S, and each two maximal left simple topological ternary subsemigroup S are disjoint. If S is compact, then each maximal left simple topological ternary subsemigroup also compact. And finally, S be a topological ternary semigroup with no zero and has at least one minimal left ideal. Then S is the union of its minimal left ideal if and only if it is a simple topological ternary subsemigroup. So here are some references. Uh, Thank you all. If you have any query or question, okay, please.
So thank you, Samanto. Is there any question from the audience? Okay. So once again, thank you. We are going for our next speaker.
Okay, thank you.
So the next presentation will be given by Mahasin Jabil Atia. So can you hear me? Yeah, I cannot hear you. You are not a bit audible. So could you please check your mic?
He is muted, sir.
So could you please unmute yourself? Hello, Atia. Could you please unmute yourself? Yeah, I can see you. Actually, your video is coming, but I cannot hear you. I cannot hear you. Okay, your voice is not coming. Unfortunately, I don't know what is the reason. I know that you're trying to fix the issue. So let's in between. Let's go for the next speaker. Once it is fixed, we will go back to you. Okay. So the next one is Lalita. Are you here?
Yes, sir. Am I audible, sir?
Yeah, yeah. So the next presentation will be given by Lalita Nerkar, and the title of the presentation is Jordan Derivation on Gamma Semi Hyperrings. So Lalita, you may start.
Okay, sir. Can you see the screen, sir?
Yes, it is visible, but your slide is not. Yeah, it's visible. Right. Yes. Right.
Good afternoon, one and all, respected chairperson Dr. Sumit Kumar Debnath, and all the participants. Myself, Lalita Pandurang Nerkar. I am a full-time research student at the Department of Mathematics, School of Mathematical Sciences, Kaviyatri Bainabai Chaudhary, North Maharashtra University, Jalgaon, under the guidance of Professor Kishore Fakira Pawar. Today's my title of paper is Jordan Derivation on Gamma Semi-Hyperring. And today I'm going to present that paper in these subsections, like first one is the abstract, then introduction, preliminaries, results, references, and then acknowledgement. Abstract is that, as I have told you, the title is Jordan Derivation on Gamma Semi-Hyperring. Gamma semi-hyperring is nothing but the hyperstructure. Then what is the hyperstructure? Hyperstructure is a natural extension of algebraic structure. Like in algebraic structure, two elements gives us the element. But in hyperstructure, two elements when operated gives us the non-empty set. That is the first part, that is a hyperstructure. Second one is the Jordan derivation. There are two concepts in my presentation. First one is the hyperstructure, second one is the derivation. Hyperstructure, I have discussed about it with you. Then derivation is the mapping holding the Leibniz product rule. Leibniz product rule, we all know about that multiplication of two elements, and if derivation is applied on that, it will be derivation of first element, second as it is, plus first as it is, derivation of second element. The same rule satisfying mapping, the mapping satisfying the same rule is nothing but the derivation. And in the present paper, I am going to introduce the Jordan derivation by equipping it with the gamma semi-hyperring, which is the hyperstructure. I will discuss with you about the Jordan derivation in um, uh, next some slides, and after that some examples and results are given dealing with that. Later on, I have collected all the Jordan derivations on that hyperstructure, which is the gamma semi-hyperring, and some arithmetic operations are applied on that collection of the derivations, and have obtained some result. That is all about the abstract. Introduction is, as I have already told you about the algebraic structure, that is a usual operation gives us the single elements, whereas the hyper operation gives us the non-empty set of the elements. That is, hyperstructure is nothing but the natural extension of algebraic structure. And this hyperstructure theory was first founded by the Marty, therefore he is the founder of the hyperstructure theory. He had presented the paper on the hyperstructure, that is nothing but the hypergroup. He initiated this study by presenting the paper on the hypergroup. Following him, Davas and other researchers have worked on the semi-group, semi-hypergroup, gamma semi-group, and they have generalized these all the three structure, and they have introduced the new hyperstructure, that is a gamma semi-hypergroup. After that, they extended the same concept to the ring, that is nothing but the gamma semi-hyperring, which is nothing but the hyperstructure, and I am going to apply that derivation on this hyperstructure. And the references are given there, that whatever I have used during my study with the help of my research guide. And then later on, the vast research work have developed on regular gamma semi-hyperring and idempotent gamma semi-hyperring. That previous slide was about all the hyperstructure. Then second topic is of the derivation. The derivation was first initiated, that is first introduced by the Posner on the ring by giving some important results on prime rings. Following the Posner, Jing applied that derivation on the gamma ring. After that, the Jordan derivation, that is the main idea of my paper, that is a Jordan derivation, one special type of derivation that was
Lalita, your internet issue may be there.
okay, sir. Okay.
Yeah.
Just
You're audible. Yes. Please continue.
okay. Am I audible now?
Yes. Please continue.
Oh, okay, sir. And I was talking about the preliminaries, which are very, very useful to understand the main or core idea of the paper. First one is the definition of hypergroupoid. Hypergroupoid means the non-empty set which is combined with hyperoperation, and that hyperoperation is nothing but if H cross H is a non-empty set with hyperoperated with same set gives us the non-empty set of the element. Therefore, that composition is nothing but a hyperoperation. And if I combine that composition of operation, that is nothing but a hyperoperation here, when it is combined with the non-empty set H, that couple is known as the hypergroupoid. If this hypergroupoid satisfy the associative property with respect to the hyperoperation, then that is known as the semi-hypergroup. Likewise, we learn in the group theory. And if the identity property, like the whatever we have learned in the group theory, if that identity property will satisfied, same here, if that identity property with the hyperoperation will be satisfied, then that semi-hypergroup will become the hypergroup. And the next definition is of the gamma semi-hypergroup. For that, we need the two non-empty set. First one is the S, we are dealing with yes, and gamma is nothing but the non-empty set of the operations. That operations I have denoted here by alpha and beta. You can take gamma and so on also. Then when it will become the semi-hypergroup, again, first one is the binary property must be satisfied there. Second one, associative must be satisfied. But with respect to what? With respect to that hyperoperation, that is x alpha y should be in S. And second one is the associative property, that is x alpha y beta z must be equal to x alpha y beta z. That is nothing but the associative property. Then it will become the gamma semi-hypergroup. Again, same gamma hypergroup, when it will become the gamma hypergroup, when that S gamma will be the hypergroup, then that S will become a gamma semi-hypergroup. And the same structure, same whatever the concept I have used, that is previously that I have used in the hypergroup, the same ring-like structure which will satisfy
Uh, Lalita, again, some issue is there. Hello, Lalita. Okay, there might be some issue. So let's look in for the. Okay. So
Now,
yes.
can I try now, Doctor?
Yeah. You please.
Okay.
Hello.
Lalita, I think has joined again. So let's complete.
Hello. Am I
Let's
audible,
have
sir?
to complete the thing. Okay. After that, you can start this.
Hello.
Lalita,
Hello.
Lalita.
Okay.
Hello. Am I audible, sir?
Yes, yes. Yeah. You are audible, but you have joined from two accounts, I think. That's why it is echo is coming.
Yes, sir. I have deliberately joined because
Okay. Right now. So you please go to your final result and conclude. Okay.
yes, sir.
Yes. So please conclude within 1 or 2 minutes, huh? Maximum.
Yes. Is it visible, sir?
Yeah, it is visible.
Okay, then these are the preliminaries, and I skipped that all the preliminaries part. And the main results are, first one is if D1 and D2 are two Jordan derivations, then D1 plus minus D2 is also the Jordan derivation. Similarly, if D1, D2 derives Dn with the n Jordan derivations, then that addition, n times addition will be again the Jordan derivation. Same for the subtraction is there. If D1 minus D2 minus D3 so on, Dn will also be the Jordan derivation. Same the next arithmetic operation is of multiplication. If D1 and D2 are the two Jordan derivations, then D1 dot D2 must also be the Jordan derivation, provided that R must be the commutative two torsion free gamma semi hyperring with characteristic 2. And last one is if I have collected all the Jordan derivations on gamma semi hyperring, and that set gives us the additive group. And future scope for this study is that whatever I have collected all the Jordan derivations forming the additive group, we want to give that additive group a new direction. All the that I do during the
Okay. Thank you,
and,
Lalita. Is there
last
any?
one acknowledgement. I'm grateful for the financial support. Mahatma Jyoti organization.
Okay. So is there any question?
Thank you all. Have a
Is there any question from the audience?
Hello, sir. Hello.
Yes.
I am Lakshman Sinkar, and my question is, Madam Lalita, Madam,
yes, sir.
what is the difference? What is the hyperstructure? Can you explain me?
non-empty set when I applied the hyper operation on that, we get the non-empty set of elements. That is in the suppose multiplication is the operation gives us 3 into 4, that is a 12. But when that multiplication is a hyper operation, we will not get the single element 12. We get the non-empty set of element. That is the hyper operation. When it is equipped with the non-empty set, that will give us the hyperstructure.
Okay, thank you, madam.
Okay, thank you, sir.
Any other question? Okay, so let's thanks to Lalita once again, and let's go for our next speaker. So the next speaker is Masin Jabel Atea. So he is going to present the paper entitled "A Resin Inverse for Unique Projection Matrices."
Okay, I will share my slide now.
Hello.
Yes, I hear you. I just try to slide my share my slide.
Yeah, sure, please.
Yes. Now, it's visible, sir.
So it is not visible.
Why?
Yeah, it's visible right now. Yeah, it's visible.
Okay. Okay. In spite of the technology issues, I would like to say today I'm so happy to present my presentation, which is under the title "A Dryzen Inverse for the Unique Projection." Before I start my presentation, I would like to say thank you so much for the organizer to give me this a great opportunity to meet you. Somebody maybe ask, who am I? My name is Mr. Jabal Atia, Mustansir University, College of Education, Department of Mathematics. In this paper, we generalize the fact that for any matrix I of order n over the complex field to compute like a result of the Dryzen inverse of A. If A is a non-singular matrix of order n, the inverse of A is the unique projection matrix X, such that rank of this matrix AIIX equal rank A. In fact, the motivation of writing this paper come from the two references, Zhang references 1 and Liu with other references 2. In fact, there are several others work on this direction, like reference 3. The main theme of this paper can be described as a study the Dryzen inverse of bounded linear operator in Banach space X, when X is the isolated spectral point of the operator. Indeed, Dryzen inverse is useful for the instance in the solution of differential equation formulated in Banach space X. Due to the elements of X rarely enter into our consideration, the exposition seems to gain in clarity when the operators are dealt with as elements of the Banach algebra of X. Additionally, the Dryzen inverse could be implied in variance application, a good illustration of this fact that application in the singular differential and difference equation, Markov chain, and other application like here, and we can find more information in references 9 and 10. In the line of investigation, Songa and other references for emphasize on the canonical form of the more Panzer and Dreisen inverse for the product difference and sum of two orthogonal generalized or hypergeneralized projection on the arbitrary Hilbert space. Investment the canonical form to examine when the more Panzer and the Dreisen inverse exist. Dong and we references 5 studied Dreisen invertibility for the product difference and sum of idempotent while other authors, specifically in references 7 and 6, applied the matrix representation of more Benzer inverse of product difference and sum of the orthogonal protection. In 1958, Dreisen introduced a different kind of generalized inverse in associative ring and semigroup that does not have reflexibility probability but commute with the element. This is her definition. Let A be elements of a semigroup, and element B is Dreisen inverse of A. We write in this formula B equal A power D if D and A have this relations for some non-negative integer k, the last non-negative integer k for which this equation hold in the Dreisen index I of A for the element A. Proceed on the square and the identity matrix and Castro with other reveal that reveal a formula of Dreisen inverse of the block matrix. This formula where A is a square. This other further they harvested representations of the Dreisen inverse of matrices of the form M. This is form M matrix A, B, C, 0, where a square under the some condition expressed and terms of the individual blocks. Permanizes founded this paper. The symbol C plus NN stands for the set of n by n complex matrices, and I belong to C by power n times n stands for the unit matrix. Little I belong to C. Then the Dreisen inverse denoted by A sub D of a matrix A is defined as a unique matrix satisfy the following relation. This is A satisfy this following relation where K here this which is represent power, where K is index of A is the index of A. In particular, if the index A equal 1, then A is called a group inverse denoted by this symbol. If A is non-singular, then index equal 0. Otherwise, index of A greater than or equal 1, especially index 0 equal 1. If A is nilpotent, then A sub D equals 0. If X is non-singular and B equal X, B X inverse, then Dreisen of B write by this way. For convenience, we write this A power pi by this equation. Use also this symbol from I to N equal from I n to M equals 0 if M less than N. Also, I denoted the unit matrix, and I sub L denoted the unit matrix of order L. Little sp denoted space comparison these matrices of order N or the complex film. For any A belong to C power n times n, we mentioned here that the definition of Dryzan inverse appeared in one to which Dryzan inverse and A. The following lemma are useful in the rest of this paper. Some details appear in the references from references 11 to 14. Moreover, little a also belong to C. We say the non-singular by this formula. We say the non-negative integer number L of k to be the index of a matrix A denoted by these symbols. Also, we will get from the previous slide, we will get this relation. Also, suppose A belong to C and index A equal K, the matrix X of order n is the Dryzan inverse of A denoted by this symbol if X satisfy the following conditions. For any matrix A belong to C power n times n, there is an inverse which A power D of A exists and is unique if index A equal K and also rank A satisfy this relation. As a matter of fact, the Jordan composition of A is defined as the following, where by this following of Jordan decomposition, where C is a non-singular matrix of order R and N is a nilpotent matrix of index A, then we have the last relation. In this section now, the Dryzan inverse of 4 unique projection matrix, the following lemma is very casual for developing the proof of main result. Little b equal this for equal matrix A B C D, where A is a non-singular matrix, then rank B equal rank A if and only if B equal C A inverse B. The first result in this section, little a belong to C power n by n, be a matrix with index A equal A, and rank A power k equal R, if X a unique project matrix of order n satisfy the relations. This is AK. A power k x equals 0, x power x times k power A power k equals 0, 2, and rank x n minus R. Then for the matrix X, there exists a unique matrix Y of order n such that rank this matrix equal rank A, and also the matrix also here this also we get this result for the matrix Y. The following theorem provides the affirmative answer to the question, which is how we can compute the Dryzan inverse of the matrix A and the matrix A power D. Therefore, during the following proof, A of alpha beta denoted R by R times R submatrix of A, which has row index set alpha and the column set beta and the n from 1 to n. Theorem 1, 2 for any A in C power n by n with the rank A equal R greater than or equal 1. Little a of let A bracket alpha br times R non-singular submatrix of A if X is unique project matrix of order n satisfy the following relation. satisfy the following relation here, this relation, we will get this result. And in this section, the derives an inverse of difference and sum of two matrices. In fact, the result of this section, modified by Leo and other authors at the reference to, we prove the result by short step. Here, this for any PQ belong to C power n by n with the index QP power P, and this is condition. Also, applying the same strategy with use the proof of the previous theorem, we can supply the proof of the following corollary. In fact, the proofs of my result require more slides, so I just give the title and the main idea and remove the proofs. Hopefully, when when my paper accept to publish in the books of journal, anyone interested in this work find all details about the subject and the result with their proofs. Finally, I closed my presentation by the list of references. It is, in fact, important reference to improve my work. Maybe any other person interested in this line and try to find more information in this way, you can depend it on some of them. Thank you so much for your good listening to my presentation.
Thank you, Atya. Is there any question from the audience? So thanks for your nice presentation. I don't think audience has any question.
Thank you so much for you. Thank you.
Okay, so let's go for our next speaker. Devapriya, are you here?
Yes, sir. Am I audible?
Okay. So yes, the next presentation will be given by Devapriya Das, and the title of the presentation is An Introduction to Strongly Clean Semiring. Yes, please. I want to just clarify the thing. Like, are you Sukhendu Kaur or Devapriya Das?
Devapriya Das.
Okay, fine. Please. Please.
Is my screen visible?
Yes, it is visible. Please press Control L. Control L.
Control L.
Yes. Now it's fine. Please proceed.
So, first of all, I would like to give special thanks to Professor Abhishek Adhikari sir for considering me as a part of this conference. My name is Devapriya Das. I am pursuing PhD under the guidance of Professor Sukhendu Kaur at Jadavpur University. So my topic is an introduction to strongly clean semiring. My contents consists of introduction, preliminaries and prerequisites, and introduction to strongly clean semiring and references. Nowadays, there is a large literature of clean ring theory, since many people are interested to study about clean ring and related areas. So the motivation behind the clean ring theory is is connected to the regularity of the ring, and a ring R is called unit regular if A equal to AUA for some unit U in R. Now, equivalently, this definition can be written as A equal to EU for some idempotent E and unit U in R. There is also another notion of regularity which is known as strongly regular, which can be given as an element A belongs to R is said to be strongly regular if there exists an element X belongs to R such that A equal to A square X with Ax equal to Xa, and this definition is equivalent to say that A equal to EU equal to UE for some E square equal to E belongs to R and U is a unit of R. Now, clean rings are the additive analogs of unit regular rings, whereas strongly clean rings are the additive analogs of strongly regular rings. Now, in 1977, Nicholson said that an element A belongs to R is said to be exchanged if there exists an idempotent E in R such that E belongs to RA and 1 minus E belongs to R of 1 minus A. In this study of exchange rings, Nicholson introduced the notion of clean rings and find a connection with exchange ring. Now, Nicholson in 1999 introduced the notion of strongly clean ring. Since then, various results of strongly clean rings have been obtained by some authors. Among different generalization of ring theory, semi-ring has become a great interest of the recent researchers. Semi-ring, a generalization of rings and distributed lattices, was first introduced by H.S. Van Diver in 1934. We have recently introduced the notion of clean semi-ring in 4, which is in the reference section. The main motivation of this article to give some characterization of strongly clean semi-ring and obtain some results related to strongly clean semi-ring. We also study the notion of exchange semi-ring, strongly exchange semi-ring, and find out their connection with strongly clean semi-ring with the help of other class of semi-rings. Preliminaries and prerequisites. In this section, we recall some basic definition. Now, what is a semi-ring? A semi-ring is a non-empty set such that with two binary operation plus and dot such that S plus is a semi-group and S dot is a semi-group with two distributive properties, left distributive properties and right distributive properties. In this presentation, we consider the semi-ring S with absorbing element 0 and multiplicative identity 1. Now, there is another type of ideal in semi-ring which is called a K ideal. A K ideal is an ideal such that which is which is equal to its K closure. Now, K closure, what is the K closure of an ideal A? K closure of an ideal A is defined by A belongs to A such that A plus A1 equal to A2 for some AI belongs to A. Now, if A equal to A K closure, then A is called a K ideal. A proper ideal A of a semi-ring is called a maximal K ideal if there is no K ideal B of S such that A proper subset of B proper subset of S. We in this presentation we denote JS means the Jacobson radical of the semi-ring, which is defined as the intersection of all maximal K ideals, and JLS denotes the intersection of maximal left K ideals. Now, let S be a semi-ring with I1 not equal to 0. We said that an element A belongs to S minus 0 is said to be left K invertible if there exists R1 such that 1 plus R1A equal to R2A. Similarly, right K invertible element is defined. Now, an idempotent element E square equal to E is said to be is said to have a complement in S if there exists an idempotent E dash in S such that E plus E dash equal to 1, and E has an absorbing complement in S if there exists an idempotent E dash in S such that E plus E dash equal to 1, E plus S E dash equal to E, and E dash plus E dash E S equal to E dash for all S belongs to S. Now, E has a strong absorbing complement E dash in S if E dash is an absorbing complement of E such that E dash equal to E dash E holds, and E has an orthogonal complement in S if there exists an idempotent E dash in S such that E plus E dash equal to 1 and E dash equal to E dash E equal to 0. Now, invertible elements are same in ring theory just defined. Let S be a semi-ring with the 0 element 0 and identity element 1 such that 0 not equal to 1. Let us define PS equal to 0 union R plus 1 such that R belongs to S. Then PS is a sub-semi-ring of the semi-ring S. A semi-ring S is said to be antisimple if S equal to PS. Now, in this section, we define exchange semi-ring. What is an exchange semi-ring? Let S be a semi-ring with identity 1 such that every idempotent of S has an absorbing complement in S, then S is said to be exchange semiring if for each x not equal to 0 belongs to S, there exists an idempotent E square equal to E belongs to S such that E belongs to S of 1 plus x closure and E1 belongs to Sx closure, where E1 is an absorbing complement of E. A semiring S is said to be strongly regular if for every R belongs to S, there exists xy belongs to S such that R square x equal to R and yr square equal to R. A semiring S is said to be strongly regular if and only if for each element R belongs to S, there exists some element Z belongs to S such that RZ are equal to R with RZ equal to ZR. In the left annihilator of an element A is defined as LA equal to S belongs to S such that A equal to SA equal to A, and the right annihilator of is defined similarly. A semiring S is called an inverse semiring if S plus is an inverse semigroup. That is, for each A there exists a unique A dash such that A plus A dash plus A equal to A and A dash plus A dash equal to A dash. Now these are the properties of inverse semirings. Now, an inverse semiring is S is called centroid semiring if for every A belongs to S, A plus A dash is in the center of S. That is, A plus A dash into B equal to B into A plus A dash for all B belongs to S. And an inverse semiring S is called additively absorbing semiring if A plus A dash into B equal to A for all A B belongs to S. An inverse semiring S is said to be an additively absorbing centroid semiring if it is a centroid semiring as well as additively absorbing semiring. Throughout this paper, E plus S denotes the set of all additively idempotent elements in S, U dash S denotes the set of all left K invertible elements in S, and S minus U dash S intersection E plus S denotes the set of all non-left K invertible additively idempotent elements in S. Now we define semipotent semiring. A non-zero idempotent E of a semiring is said is a primitive idempotent if for any non-zero idempotent F of a such that F belongs to AC closure implies SF closure equal to AC closure. Now a semiring S is said to be local semiring if it has unique maximal K ideal, and an idempotent E of S is said to be local idempotent if the corner semiring AC is local. A semiring S is called a clean semiring if every non-zero element can be written as the sum of an idempotent and the unit, and it is called strongly clean if it is a clean semiring and with EU equal to UE holds. Every commutative clean semiring is a strongly clean semiring. And in the definition of clean semiring and strongly clean semiring, we exclude the element 0 because if 0 can be written as the sum of an idempotent and unit, then it becomes the ring. And already many works have been done on clean ring and semi-clean ring. So we want to work on proper semiring. So we exclude in the definition of clean ring and strongly clean semiring the element 0. Now these are the examples of strongly clean semiring. Every semi-field is an example of a strongly clean semiring. Similarly, division semiring, and this is the finite semiring we construct S equal to 0, 1, 2, 3 with two binary operation plus and dot as defined. Here, every non-zero element can be written as the sum of a unit and idempotent, and they are commuting. This is also an example of strongly clean semiring, which I product with a division ring. So the resulted semiring is a proper semiring. Uh, Now, this is also an example of strongly clean semiring. Now these are the two basic results of strongly clean semiring. That is, every homomorphic image of a strongly clean semiring is strongly clean, and the finite direct product of strongly clean semiring is strongly clean. Now let S be a strongly clean centroid semiring such that every idempotent of S has an orthogonal complement in S. Then the corner semiring ESE is strongly clean for all E square equal to E belongs to S. Nicholson proved that a strongly clean semiring with identity 1 is always an exchange ring, and the converse holds if idempotents are central. But in semiring theory, this does not hold. Let S be a strongly clean inverse semiring such that every idempotent has an absorbing complement in S. Then S is an exchange semiring. But the converse of theorem 3 is not true even if the idempotents of S are all central, which follows from the example we construct the subset of natural numbers 1, 2, 3, 6, and we define two binary operation meet and join such that A meet be equal to GCD of AB and A join be equal to LCM of AB. Then S is a bounded distributive lattice and hence a semi-ring. Now S is an inverse X in semi-ring, but S is not strongly clean semi-ring. This is the Hasse diagram of S. Now, a semi-ring is said to be semi-potent if every non-zero left k ideal I of S that is not in contained in JLS contains a non-zero idempotent. Let S be an inverse extend semi-ring such that the set S minus U dash S intersection E plus S is contained in every non-zero principal left k ideal of S, then S is semi-potent. Let S be an inverse semipotent semi-ring such that the set S minus U dash S intersection E plus S is contained in every non-zero principal left k ideal of S, then every primitive idempotent is local. From proposition 2 and proposition 3, we have the following theorem. Let S be a strongly clean inverse semi-ring such that every idempotent has absorbing complement in S, then the set S minus U dash S intersection E plus S is contained in every non-zero principal left k ideal of S, then every primitive idempotent is local. Let the converse of the theorem 5 is not hold, which follows from the example. We consider the set of all non-negative integers and define two operation plus and dot on S by a plus b equal to max of a b and a dot b equal to usual multiplication. Then the local the primitive only primitive idempotent is 1 and 1 s 1 equal to s is local, but s is not strongly clean semi-ring. Basically, the sum analog of strongly regular ring is strongly clean, and every strongly regular ring becomes strongly clean ring. But in semi-ring, it is not happen, which follows from the example one. But under some condition, a strongly regular semi-ring is strongly clean ring, which follows from the next theorem. Let S be an anti-simple strongly regular semi-ring such that every idempotent of S has a strong absorbing complement. Then S is a strongly clean semi-ring. But the converse of theorem C does not hold, which follows from the example. We take S1 equal to the set of all non-negative integers, and we take a k ideal I equal to 4 and 0 plus. Then we take the quotient set, that is the set of all congruence classes S dash equal to 0, 1, 2, 3, which becomes a semi-ring under the operation of operation of congruence classes. But S dash is a strongly clean semi-ring, but S dash not a strongly regular, as 2 cannot be written as 2 equal to 2 square into A for any A belongs to A dash. Now let S be an additively absorbing centroid semi-ring and A belongs to S such that EA equal to A for some idempotent E in S, then the following conditions are equivalent. That is, AE has a multiplicative inverse in EAC, E belongs to SA closure, and LA is a subset of LE. LM is the left annihilator of it, and 3 is E belongs to AS closure, and RA is a subset of RE. RA means the right annihilator of A. Now we define strongly exchanged semi-ring. Let S be a semi-ring such that every idempotent has absorbing complement in S. Then S is called strongly exchanged semi-ring if for each AE in S the following holds. That is, E plus S is a subset of closure means the principal k ideal generated by principal left k ideal generated by A, and there exists an idempotent E1 belongs to S with absorbing complement E such that E1A equal to A E1, and E1 belongs to S of 1 plus A closure and E belongs to SA closure. And third condition is L of 1 plus A is a subset of AC closure and LA is a subset of AC1 closure. Finally, by using lemma 2 and definition of strongly exchanged semi-ring, we have the following characterization of strongly clean semi-ring. Let S be an additively absorbing centroid semi-ring, then S is strongly clean if and only if S is strongly exchanged semi-ring. Now let S be a semi-ring with no non-trivial idempotence, means 0 and 1 are the only idempotents.
Excuse me, please. Could you please conclude within 2 minutes?
Yes, sir. Yes, sir.
Okay.
Let X plus X belongs to JLS. JLS means the intersection of maximal left K ideals for all X belongs to S minus U dash S, where U dash S is the set of all left K invertible elements is S. Then the following are equivalent. S is a local semi-ring, S is an exchange semi-ring, and S is a semi-potent semi-ring. So let S be a semi-ring with no non-trivial idempotence. let x plus s belongs to GLS for all x belongs to s minus u dash s, then S is local, extend and semi-protein semi-ring if S is a strongly clean semi-ring. But the converse of theorem 11 is not true, which follows from the following example. Here we construct the example by taking the set of all non-negative integers and taking the prime k ideal 2n0 plus. Then we localize S at P, which is the localization of S at P, which consists of the equivalence classes m by n such that m belongs to S and n belongs to S minus P. Then SP is a commutative semi-ring with respect to the following binary operation. Here SP is a local semi-ring because 2n0 plus is the only maximal k ideal of S, but SP is not a strongly clean semi-ring. So if S is a semi-ring with no non-trivial idempotence such that x plus s belongs to JLS, then the following implications should now be clear. A clean semi-ring, strongly clean semi-ring. Strongly clean semi-ring means local semi-ring, but local semi-ring does not mean strongly clean semi-ring, and the extended semi-ring and semi-protein semi-ring are equivalent. So this talk based on the papers. And Quad SD dash D, this clean semi-ring, this is the publication of my paper. So thank you.
Thank you, Devapriya. Is there any question from the audience? So once again, thank you, Devapriya, for nice presentation. Let's go for our next speaker. Malay, are you present?
Yes, sir. Am I audible?
Yes.
Sumit, Sumit,
yes,
just
yes.
with your permission, I just one announcement.
Yes, sir. Sure.
Is there anyone from 3B? Is there anyone from 3B here? I can see that Kaji Abu Rosen is here.
Yes, sir.
So, but I think your presentation is in 3B, right? This is 3A. So could you please just go to the next other parallel session? So I will just share.
Okay, sir.
I have already sent you this email. In that email, you can check, or I can share.
Yes.
Okay. And anyone else is there who is in 3B? So yeah. So okay. And Professor von Rosen, are you here? Can you hear me, Professor Rosen? Okay, I think Professor Rosen is not here. Okay. Anyway, thank you. Sorry for the interruption. Yeah, please continue.
Okay, sir. Thank you.
So can I share?
Yeah, please. Just a minute. Right now, Malay Payne is going to present the paper entitled "Extended Weak Symmetry Structures." Malay, you may start.
So it is visible?
Yes, it is.
Okay. So according to our geographical location, good afternoon, good evening, and good morning, everyone. And I also want to thank Dr. Abhishek Odhikari and Sumit Kumar Devnath to give me a presentation here. So here I will talk about today I will talk about extended weakly symmetric structure, and I am a research scholar, Department of Mathematics, Bankura University. So my outline of the presentation is, at first I will introduce some basic definition, and after that using this definition we'll see the lemma and preposition, and which will help us to prove our main theorem. Then we will go to the next slide, basic properties of extended weakly symmetric structure. After that, we will go to the general form of curvature tensor of in extended weakly symmetric space. Finally, we will see the existence of extended weakly symmetric space by one example. So at first introduction, in 1889, Tamasebin was first introduced weakly symmetric space, and it says that a semi-Riemannian manifold is said to be weakly symmetric if covariant derivative of Riemannian curvature tensor can be expressed in terms of three one forms, like as A, B, D. Here A, B, D are one forms, that is 0, 1 tensor. Okay, so after then we include here, we extend weakly symmetric manifold. The definition of extended weakly symmetric manifold says that a n-dimensional semi-Riemannian manifold is said to be extended weakly symmetric manifold if covariant derivative of Riemannian curvature tensor can be expressed in 15 one forms. They are A, B, B bar, D, D bar, alpha, beta, beta bar, and so on. There are all of the one forms, 15 one forms. Here G is a Gaussian curvature tensor, which is a 0,4 tensor. And the special case of curvature restricted geometric structure are the symmetric space, and this is introduced by Cartan in 1926. And if all the 15 components, that is A, B, all the components are 0, then the space is symmetric. That is covariant derivative of R equals to 0, then the space is symmetric space. And MSAST in 1987, he will introduce the definition of pseudo-symmetric space. And if the first component is 2A and 4 component is A, and the other 10 component is 0, then the space is pseudo-symmetric space. Similarly, generalized pseudo-symmetric recurrent space, weakly symmetric space, and generalized weakly symmetric space. And this is the definition of generalized weakly Ricci symmetric manifold. If a n-dimensional semi-Riemannian manifold is said to be generalized weakly Ricci symmetric manifold if covariant derivative of Ricci tensor can be expressed in terms of 6 one forms. They are A, B, D, alpha, beta, delta. Okay, and the basic preliminaries here. The lemma 2.1, which says that if K is a generalized 0,4 tensor in a semi-Riemannian manifold which satisfy equation 2.1, then either A is 0 or K is 0. Okay, and using in this way, the main idea behind this proof is if you contract x1 and x2, you can easily prove that A is 0 or K is 0. Using 2.1, we can deduce lemma 2.2, and this says that in a semi-Riemannian manifold, if we say semi-Riemannian manifold which satisfy equation 2.2, then either M is a constant curvature, that is R is equals to some scalar multiple of Gaussian curvature, or A, B equals to 0. And the proposition 2.3, which says that in a semi-Riemannian manifold M which satisfy equation 2.3, then either M is a constant curvature or Einstein manifold, or it is a conformally flat, that is C equals to 0, or A, B, D equals to 0. Okay, that is all the one form as 0. And it's due to short time, I will unable to explain this proof, but if you give me more time, I will explain this proof. So after this presentation, but the main idea behind this proof is if you contract x1 and x2, and this is the sketch of the proof. If you contract x1 and x2, you can after that equation lemma 2.1 and 2.2, you can easily prove this proposition. Okay, so the next part is the basic properties of extended weakly symmetric structure. Since we know that R is Q symmetric with respect to first two components, that is x1 and x2, and using 1.1, we have this equation. And the previous proposition 2.3, if we get there B equals to B bar, or beta equals to beta bar, or phi equals to phi bar. Since R is Q symmetric with respect to last two component also, then similarly we can get D equals to D bar, psi equals to gamma bar, psi equals to psi bar. And so we say that the theorem, if M is a non-conformally flat proper extended weakly symmetric manifold, then in the equation 1.1 reduces to 9 components. There are 15 components, and here B equals to B bar, so B is same. D equals to D bar, so D is same. And beta equals to beta bar, so beta is same. Gamma equals to gamma bar, gamma is same. Psi equals to psi bar, psi is same. And phi equals to phi bar, so they are same. And this is equation 3.1, which has 9 one forms. Okay, after this equation, if we contract x1 and x2, then we get the Ricci tensor, covariant derivative of Ricci tensor, and which gives this form. And this is, they are say 6 plus 2, total 8 8 terms. If last two term is zero, then it reduces to generalized weakly Ricci symmetric space. In previously in equation 1.2, you can see that there are 1.2, there are six terms, 1 2 3 4 6 terms. So if you see the last two term is zero, then the equation extended weakly symmetric space reduces to generalized weakly Ricci symmetric space. Okay, so the form of curvature tensor of extended weakly symmetric space. In Bianchi's second identity, we know that the covariant derivative of R in cyclic order, sum of all cyclic order, is zero. Here note that x3, x4 are fixed. X3, x4 are fixed, and x5, x1, x2, they are cycle form x5, x1, x2, x1, x2, x5, and x2, x5, x1 equals to 0. And using 3 point before equation, using 3.1, we have this after the calculation, just basic calculation, we have the equation 4.4. Equation 4.4 is our main theorem. This says that the extended weakly, this is the generalization form of Riemannian curvature tensor in extended weakly symmetric space, and it is a 0,4 tensor because G is a 0,2 tensor, S is a Ricci tensor which is also 0,2, and G is J, so 0,4 tensor. Similarly, G is a 0,2 into 0 wedge, so 0,4 tensor. Similarly, the other two part is 0,4 tensor. So R is a 0,4 tensor, and J is a non-null vector field. Okay, so this is the case, and from this we can reduce the corollary, the weakly symmetric manifold associated with one form ABD, and this looks like this, and the generalized weakly symmetric manifold with associated one form ABD alpha beta, and this looks like this. And this is the existence of extended weakly symmetric manifold. So we'll see that if R4, consider R4 with together with 0,2 tensor and considering the metric, which is the equation 5.1, and this shows that the space is satisfy the condition extended weakly symmetric space, and all the component you can see that are non-zero, and it shows that the existence of this space. So here we see that the space extended weakly symmetric space is we extend the concept weakly symmetric space to extended weakly symmetric space, and also we see that the spaces exist by an example. So this is our main conclusion. Thank you, and this is few references. Thank you. If you have any question, you can ask me.
Malay, thank you. Is there any question from the audience?
So can I stop my slide?
Yes. So thanks once again for the nice presentation. Now,
thank you, sir.
We're going for our next speaker, in Vera.
Yes, sir.
Okay.
I am here. Sir, I am audible?
Yes, you are.
Okay.
So
Sir.
right now, in Vera is going to present the paper entitled "A Result Concerning B Generalized Q Derivation on Multilinear Polynomials in Prime Rings." Vera, you may please start.
Okay, sir. Sir, my screen is visible?
Yes, it is. Please.
I am Nipendu Bera, a PhD scholar of Jadavpur University under the supervisor Sukhendu Kaur. The title of my paper is A Result Concerning B-Generalized Q Derivation on Multilinear Polynomials in Prime Rings. These are the outline of my presentation. Introduction. Ring derivation is a branch of algebra in which we study about the structure of an additive map as well as the structure of a ring by analyzing some functional identities involving additive maps. These additive maps are derivations, Q derivation, generalized derivation, generalized Q derivation, B-generalized derivation, multiplicative generalized derivation, multiplicative in bracket generalized derivation, etc. It is well known that there is a strong relationship between the functional identities involving derivation and generalized derivation and the structure of the ring. In this article, we find the structure of two bizarrely skewed derivation by analyzing a functional identity. There are some notation. First of all, R is denoted by denote the prime ring characteristics different from zeta, the center of R. QR with the martindale, right martindale quotient ring of R, that is the extended ring of the prime ring R, and C with the extended centroid of R, that is the center of the right martindale quotient ring QR, and the simple commutator x comma y is equal to xy minus yx, and the second commutator x comma y is equals to xy square minus 2yxy plus y square x. There is a definition. First of all, derivation. The derivation of a ring R is an additive mapping d R to R such that d of xy equals to d of xy plus x dy holds for all x comma y belongs to R. Generalized derivation. An additive mapping if R to R is called generalized derivation if there exists a derivation d such that f of xy equals to f of x y plus x dy holds for all x comma y belongs to R. Skew derivation. A linear mapping d R to R is said to be a skew derivation if there exists a automorphism alpha on R such that d of xy equals to d of xy plus alpha x dy holds for all x comma y belongs to R. Generalized skew derivation. A linear mapping f R to R is said to be a generalized skew derivation if there exists a skew derivation d and an automorphism alpha on R such that f of xy equals to f of xy plus b alpha x into dy holds for all x comma y belongs to R. There are some motivation by which we motivated to study this paper. In 2012, Carini and De Filippis proved that if R is a prime ring of characteristics not 2 and U be the Utumi quotient ring of R, delta be the non-zero derivation of R, G be a non-zero generalized derivation of R, and F a non-central multilinear polynomials over C, such that delta of g of f of x into f of x equals to 0 for all x belongs to Rn, then there exists a comma b belongs to U, E with the Utumi quotient ring of R, the extended ring of R, such that g of x equals to ax and delta x equals to first order commutator b comma x for all x belongs to R with first order commutator b comma a equals to 0, and f square is central valued on R. In 2014, Dhara and De Filippis gave a complete description of the generalized derivation f and g when f and g satisfied f square f of x into f of x minus f of x into g square f of x equals to 0 for all x belongs to In, where I is a non-zero two-sided ideal of R. Also, after this, De Filippis and Scudo and Wing studies this situation replacing f square and g square with two bizarrely skewed derivation in prime rings. In 2016, Dhara, Ark and Abbas described the structure of the additive maps D, F and G satisfying D of f of x into f of x minus f of x into g of f of x equals to 0 for all x belongs to Rn, where f is a multilinear polynomial over extended centroid C and D is a non-zero derivation, and f comma g are two generalized derivation on the prime ring R with characteristic not 2. In 2016, Dhara and Ark extended the above result, replacing the derivation delta with another generalized derivation f, that is f of g of f of x into f of x equals to 0 for all x belongs to In, and then they give a complete description of the additive maps f and g, where I is a non-zero two-sided ideal of R. After this, 2022, Dhara, Kaur and Kuila studied the case d of f square f of x into f of x is equals to f of x into g square f of x for all x belongs to In, and obtain the forms of the map f and g, where f and g are two generalized derivations. In a recent paper, Prajapati and Gupta studied first order commutator a comma f of x into f of x belongs to center for all x belongs to Rn, where f is a bizarrely skewed derivation of R. Motivated by the above previous work, we study for the identity first order commutator a comma f of x into f of x is equals to f of x into g of x. Here a is a a belongs to R minus zeta, and f comma g are two B generalized Q derivation of R. More precisely, we study the theorem, let R be a prime ring and of characteristic difference from 2, zeta its center, QR its right material quotient ring, C be the extended centroid, and F a non-central multilinear polynomial over C, with B belongs to QR and F, G are two B generalized Q derivation of R. If there exists A belongs to R minus zeta such that first order commutator A, F of x into F of x equals to F of x into G of F of x for all x belongs to Rn, then F square is a central value of R, and there exists P, Q belongs to QR such that F of x suman P of x, G of x suman x cube for all x belongs to R with first order commutator A, P is equals to Q. In particular, if we consider G equals to 0, then we can get the following corollary. Let R be a prime ring of characteristic not to QR be the right material quotient ring, C be the extended centroid, and B belongs to QR. Suppose that F be a B generalized Q derivation of R and A does not belongs to zeta, such that first order commutator A, F of x into F of x equals to 0 for all x belongs to Rn. Then there exists P belongs to QR such that F of x suman Px for all x belongs to R with F square is a central value of R and first order commutator A, P equals to 0. Also from the main theorem, we can get the corollary 1.2. Let R be a prime ring of characteristic not to QR its right material quotient ring, C be the extended centroid of R, and B belongs to QR. Also let F be a multilinear polynomial over C, which is not a central value of R. Suppose that F and G be two B generalized Q derivation of R such that first order commutator F of U into U, G of V into V equals to 0 for all U, V belongs to F of R, where F of R defined by this way. Then there exists P, Q belongs to QR such that F of x equals to P of x and G of x equals to Q of x for all x belongs to R with F square is a central value of R and first order commutator P, Q equals to 0. These are my references of this paper. Thank you.
No. Is there any question from the audience? Okay, then thanks to Invera.
Thank you, sir.
For your nice presentation. Let's go for our next speaker, Alamgir Hossain.
Yes, sir, I am here.
Okay, good. So right now, Alamgir Hossain is going to present the paper entitled Fractal Interpolation Functions and Recent Development. Alamgir, you may please start.
Yes. Yes, sir. It is visible?
Yes, it is. Please.
Yes. So my name is Alamgir Hossain from Presidency University. Today, I am going to deliver a presentation on fractal interpolation function and recent development. So first of all, we impose two questions. This is a very interesting question, and it is easy to understand. For a given data set, xi, yi in R2, can we construct a interpolation function which is no high differential? And next question is, if f is a function from interval ab to r which is continuous, can we approximate f by a no high differential function? So first we impose two questions and we provide the answer of these two questions. Preliminaries. Hausdorff-metric. Let K is a subset of R2 and script Sk is denoted the class of all non-negative complex subset of K. And Hausdorff-metric is given by a small a of AB is maximum of distance between the set A and B and distance between the set B and A. And this ace is give a metric on the space script ask. And if KD is the complete metric space, then script ask ace is also a complete metric space. And next, iterated function system. Iterated function system nothing but a collection, finite collection of continuous function. And if the maps are contractive with the contractivity factor Ci, where Ci lying between the closed 0 and open 1 interval, then this IFS system is called the hyperbolic iterated function system. Hutchinson operator. The Hutchinson operator is a shared valued function from script ask to script ask, which is given by W of A is equal to union of Wi of A, where I are the contraction map for all A belong to script K. And this is well defined because Wi are the continuous map and A is compact. So this Wi is compact and union of a finite compact set is compact. So this is well defined map. Now the theorem says that if the map Wi are all contractive map, then the Hutchinson operator W is also the contractive map with respect to the contractivity factor C, where C is the maximum of Ci. And hence it has an unique fixed point by Banach fixed point theorem, because script Hk is the complete metric space with respect to the hydrometric. And this fixed point is given by limit n tends to infinity Wn of A for all A belonging to script K. So we will see that and this fixed point is called the attractor of this IFS. So we'll see an example. If we consider W1 is x by 3 and W2x is equal to x by 3 plus 2 by 3, then the fixed point is nothing but a contour set. If we apply the W1 on the interval 0, 1, then we get, if we put here x is equal to 0, then we get 0, and x is equal to 1, then we get 1 by 3rd. So we get this interval 0 to 1/3. And if we apply W2, then we get 2/3 and 1. And again, if we apply the W1 here, then we get 0 to 1 by 9, and so on. So ultimately, we get a fixed point of this IFS system, and this IFS fixed point is nothing but a Cantor set. Similarly, we give an example of a Sharp-Pinkston triangle. If we consider a triangle with vertices 0, 0, 1, 0, and half, 1, and we apply those three IFS, F1, F2, F3. If we apply F1 here, then we get this triangle, and F2 here, then we get this, and F3, then we get this, and so on. And finally, we get the Sharp-Pinkston triangle, which is the attractor of this IFS system. Now we discuss about the fractal interpolation function. If xi or y are the given data set, and where x0 is strictly less than equal to x1, strictly less than equal to xn, then we consider the IFS R2Wn, where Wn is the affine transformation, which is given by is this form an0 cndn plus enfn, and it can be written as lnx fn x comma y, where lnx is anx plus en and fn xy is equal to cnx plus dny plus, and which satisfies the join-up condition wn x0 y0 is equal to xn minus 1 yn minus 1. See, if we put here a w1, then x0 y0 going to x1 y1, and similarly if wn of xn yn is equal to xn yn. So we'll see a picture what happened here. If we consider a unit square 0, 1 cross 0, 1, and if we apply the W1 map here, then we get the parallelogram, this parallelogram, W1 of K. And if we apply the W2, then we get this. And if we apply the W3, then we get this. And similarly, if we apply continuously in this parallelogram, W1, W2, and W3, then we get this W1 of W1K, W2 of W1K, W2, 3 of W1K, and so on. So ultimately, we get this attractor of that IFS. And this Barnes shows that this is nothing but a graph of a continuous function. And here we'll see that if we consider Dn actually Dn lies between the 0, close 0, and open 1. And if we consider dn tends to 1, then this graph becomes more complicated. And so the graph is the function is no higher differentiable. Next, in particular, if we consider if we fixed a function f, and if we consider fn xy is equal to alpha n y plus f compose ln x minus alpha n bx, where alpha n is scalar between its mod value is strictly less than 1, and b is a continuous function which satisfies those conditions, and b not equal to f, then the IFS system, which is this case proposed by M.F. Barnsley, and this IFS system, if this IFS system satisfies the join-up condition wn x naught y naught is equal to x n minus 1, f of x n minus 1, and so on, then this IFS system has an attractor, and which is nothing but a graph of a continuous function. And this function is called the alpha fractal function, which is denoted by f alpha. So this is the figure. If we consider the classical function f, and if we and the corresponding alpha fractal the graph of corresponding alpha fractal function is this, which is approximate this function. Next, we provide some reference here, and thank you.
Okay. Is
Yes.
there any question from the audience? Okay, Alamgir, thanks for such a nice presentation. And if there is no question, then we can move for the next speaker. The next speaker is Moinak Mitro. Are you here? Moinak? Okay. Then Chapikul Mia, are you here?
Yes, sir.
Okay. So right now, Mr. C. Mia is going to present the paper entitled "A Study on Eye-Open Sets and its Related Homomorphic Images." Mr. Mia, you may please start.
Am I audible, sir?
Yes, yes.
Good afternoon to all dignitaries presented here. First of all, I would like to thank Professor Abhishek Kodikari and Chairperson Professor Sumit Kumar Devnath for considering me as a presenter. I am Sapikul Mia, Assistant Professor, Department of Mathematics, Sukanta Mahavidyalaya. I am going to present a new type of eye-open sets and its related homeomorphic images. This is a joint work with my supervisor, Professor Shamapada Modak. This section contains preliminaries, my main topic works, and the references. Before going to discuss my main section, I am going to discuss some definition and results related to this work. Definition: ideal. Let capital X be a non-empty set. A collection of subset of X is said to be ideal if I is closed under finite union, and if A belongs to I and B subset of I implies B belongs to I. Let X comma tau be a topological space and I be any ideal on X, then the structure X tau I is called an ideal topological space. Let X tau I be an ideal topological space, a subset of capital X, and let capital A be a subset of X. The local function of A with respect to I and tau is defined by those X belongs to capital X such that A intersection U belongs to I for every open set U containing X. We'll simply write A star or A star with respect to I comma tau. This local function helps determine some new type of topology on X. One of them is called star topology. The basis of the star topology is of the form A set difference I such that M belongs to tau and I belongs to capital I. The members of star topology is called star open set. Next, we give the definition psi operator. Let x tau I be an ideal topological space and capital A be a subset of x, then psi operator on x tau I is defined by psi A is equal to x set difference A star for any A subset of capital X. Now we give the definition I open set, which is important in this talk. Let x tau I be an ideal topological space. A subset M of capital X is called I open set if M subset of int M star, which is given by Jankovic. The set of all I open sets in an ideal topological space is denoted by simply IOX. Now the definition of main section. Maximal I open set. This is my works. A proper non-empty subset capital M of X in an ideal topological space is called maximal I open set if it is an I open set and every I open set which contains capital M is either capital X or M. If we consider the ideal topological space X tau I, where X is equal to E1, E2, E3, E4 and tau equal to phi X, E1, E2, E3, E1, E2, E3 and the ideal is equal to phi E2, then E1, E2, E3 and E1, E3, E4 are maximal open sets in this space. Again, if you consider an ideal topological space X tau I, where capital X is the set of real numbers and the topology tau is equal to phi close interval AB R, where L is equal to B and the ideal A and phi A, then A comma B semi open is a maximal I open set. Now we have to show that every I open set may not be a maximal I open set by the given example. If we consider the ideal topological space X tau I, where capital X is the set of all real numbers and tau is equal to phi ABR and the ideal is equal to phi singleton set A, then close interval AB is a star open set but not a maximal I open set. The set of all maximal I open sets in an ideal topological space we denote it as M max IOX. Now we have to show that maximal I open set and my maximal I openness are independent concepts. For this, if you consider X tau I is an ideal topological space and where X equal to E1, E2, E3, E4 and the topology tau is equal to phi X, E1, E2, E3, E1, E2, E3 and the ideal phi E2, then E1, E3, E4 is a maximal I open set, but this is not a maximal open set. Every ideal topological space maximal I open set may not exist. If an ideal topological space has a maximal I open set, then this ideal topological space is denoted as SM max IOX. Here we consider an ideal topological space where this structure, this topological space has no maximal I open set. If we consider X equal to E1, E2 and the topology tau equal to phi X E1 and the ideal phi E1, then this ideal topological space has no maximal I open set. Lemma. Let X tau I be a maximal I open set. Let X tau I be an ideal topological space with maximal I open set, and if M is a maximal I open set and O be an I open set, then either M union O is equal to the whole set or O subset of M. And if we take M and N be two maximal I open set, then either M equal to N or the union of these two maximal I open set is equal to capital X. Corollary, the union of two maximal IUPAC set, that means either a maximal IUPAC set or whole set capital X. Here, this is an example, a topological space which have no maximal IUPAC sets. Theorem, let X tau I be an ideal topological space and let M1, M2 be three maximal IUPAC sets with M1 not equal to M2, and if M1 intersection M2 subset of M3, then either M1 equal to M2 or M2 equal to M3. And this is an important result we have already proved. Let X tau I be an ideal topological space and M1, M2, M3 be three members of M max IOX, then such that they are different from each other, then M1 intersection M2 is not properly contain M1 intersection M3. I neighborhood, a subset of an ideal topological space is called I neighborhood of a point X if there exists an IUPAC set containing X and contain this set. We have proved that every I neighborhood is an IUPAC set in an ideal topological space. Next proposition, let X tau I be an ideal topological space with maximal IUPAC set, and if M is a maximal IUPAC set and P belongs to M, then M can be expressed as union of all IUPAC set containing P such that NP union M not equal to X. Now we have to show that the presence of proper maximal IUPAC set. For this, we consider cofinite IUPAC set. Cofinite IUPAC set means those IUPAC sets whose complement is a finite subset. We have proved that if capital O is a proper non-empty cofinite IUPAC subset in an ideal topological space X tau I, then there exists at least one cofinite maximal IUPAC set M such that a O subset of M. Next, we have proved in an ideal topological space X tau I with maximal IUPAC set, and if M is a maximal IUPAC set and P is any member of M complement, then X set difference M subset of W for any I neighborhood of P. Corollary, let X tau I be an ideal topological space with maximal IUPAC set and M is a maximal IUPAC set, then one of the following are true. For any P belongs to X set difference M and for each W belongs to INP, then W equal to X, or there exists an IUPAC set M such that X set difference M subset of W and W is a proper subset of capital X. We get next corollary, let S M X IUX, that is maximal, that is ideal topological space with maximal IUPAC set, and M is a maximal IUPAC set, then the following at least one of these hold. Next part, we have discussed the images, homeomorphic images of maximal IUPAC set. For this, we have used the following lemma. Jankovic 1992 discovered let F maps X to Y be a function, and if I is an ideal on X, then Fi is equal to those Fi1 such that I1 belongs to capital I is also an ideal on capital Y. And if F maps X to Y be an injective function, and if I is an ideal on Y, then F inverse I contains those inverse I1 such that I1 belongs to capital I is also an ideal on capital X. We have used this proposition. These have already proved. Let X tau 1 and Y tau 2 be two topological space and I be an ideal on X, and if F maps X to Y is a homeomorphism, then for any M subset of capital X, Fm star with respect to Fi is equal to F of M star with respect to the ideal I. We have get the following results. Let X tau 1 and Y tau 2 be two topological space and I be an ideal on X, and if F maps X to Y is a homeomorphism, then for any IUPAC set M in X, Fm is also an Fi open set in Y. Next result, let x tau 1 and y tau 2 be two ideal topological space and I be an ideal on X, and if F maps X to Y is a homeomorphism, then for any I open set M in Y, F inverse M is also an F inverse I open set in capital X. We prove the following theorem. Let x tau 1 and y tau 2 be two topological space and I be an ideal on X. If F maps X to Y is a homeomorphism, then for any maximal I open set M in X, Fm is also maximal Fi open set in X. That is, maximal I open set is invariant under homeomorphism. Similarly, let x tau 1 and y tau 2 be two topological spaces and I be an ideal on Y. If F maps X to Y is a homeomorphism, then for any maximal I open set M in Y, F inverse M is also maximal I open set in X. Remarks: if F maps X to Y is a function, then the above theorem may not be always true. That is, for any maximal I open set M in X, Fm is not always a maximal Fi open set in Y. For this, we consider the following examples. For this, let x tau 1 I be an ideal topological space where capital X equal to E1, E2, E3, E4, tau 1 equal to phi x, E1, E2, E3, E1, E2, E3, and the ideal I equal to phi E2, then M equal to E1, E2, E3 is a maximal I open set. And if you consider y tau to be another topological spaces where y equal to x and tau 2 equal to tau 1, and define a function f maps x to y by f E1 equal to E1, F E2 equal to E2, F E3 equal to E2, and F E4 equal to E3, then Fm is not a maximal Fi open set in Y. Next, the lemma we have already that have already proved. Rubiano 1918. Let F maps X to Y function, and if I is an ideal on Y, then F forward arrow I those A such that A subset of F inverse I1 belongs to F inverse the ideal is also an ideal on X. For this, using this lemma, we have proved that let X tau 1 and y tau 2 be topological spaces and I be an ideal on Y, and if F maps X to Y is an injective function, then F inverse I is equal to F forward arrow I. And we have proved the following lemma using this proposition. Let x tau 1 and y tau 2 be two topological spaces and I be an ideal on Y, and if F maps X to Y is a function, then for any maximal I open set M in Y, F inverse M is not always a maximal F forward arrow I open set in X. We give the example corresponding to the above remarks. If you consider y tau to I be topological space with an ideal where y equal to E1, E2, E3, E4, and the topology tau 2 equal to phi x1 and the topology phi x E1, E2, E3, E1, E2, E3, and the ideal I equal to phi E2. Therefore, M equal to E1, E2, E3 is a maximal I open set in Y. Again, if you consider another topological space, T space means topological space x tau 1 where x equal to E1, E2, E3, E4, and tau 1 equal to tau 2, and define a function f maps x to y by f E1 equal to E1, f E2 equal to E2, f E3 equal to E4, if E4 equal to E3, then F inverse L is not a maximal F forward arrow I open set in X. This is the references for this results. Thank you, sir.
Okay, thank you, Mia. So is there any question from the audience? Okay, then once again, thank you, Sapikul.
Thank you, sir.
Let's go for our next speaker. Anjan Bhattacharya, are you here?
Yes, sir, I am here.
Anjana, sorry, it's my mistake. Sorry. Right now, the Anjana Bhattacharya is going to present the paper entitled P regular space in fuzzy setting. Anjana, you may start, please.
Okay, sir. Good evening, everybody. My topic is P-star pre-regular space in fuzzy setting. Outline. In this paper, we introduce a new type of fuzzy regular space, namely fuzzy Pister pre-regular space, by introducing a new type of open set, namely fuzzy Pister pre-open set, the class of which is strictly larger than that of fuzzy open set. It is shown that in this space, fuzzy open set and fuzzy Pister pre-open set coincide. Also here we introduced two new types of functions, fuzzy Pister pre-continuous and fuzzy Pister pre-irresolute functions. Some applications of these two functions on this newly defined space are shown here. First, to recall the definition of fuzzy pre-open set. Fuzzy pre-open set was introduced by H. Nanda. A fuzzy set A is called fuzzy pre-open if A less than equal to interior closure A. The complement of this set is called fuzzy pre-closed set. The union of all fuzzy pre-open sets contained in a fuzzy set A is called fuzzy pre-interior of A, denoted by P int A, and intersection of all fuzzy pre-closed sets containing a fuzzy set A is called fuzzy pre-closure of A, denoted by PCLA. A fuzzy set A is fuzzy set A in an FTSX is called fuzzy pre-neighborhood of a fuzzy point X alpha if there is a fuzzy pre-open set U containing X alpha contained in A. Now we recall the definition. We introduce the definition of fuzzy Pister pre-open set. A fuzzy set A is called fuzzy Pister pre-open if A less than equal to pre-interior closure A. Complement of this set is called fuzzy Pister pre-closed set. The union of all fuzzy Pister pre-open sets contained in a fuzzy set A is called fuzzy Pister pre-interior of A, denoted by Pister P int A, and intersection of all fuzzy Pister pre-closed sets containing a fuzzy set A is called fuzzy Pister pre-closure of A, denoted by Pister PCLA. Union of two fuzzy Pister pre-open sets is also shown, but intersection of two fuzzy Pister pre-open sets need not be shown follows from the next example. This is the example. So we conclude that for a set of all fuzzy Pister pre-open sets do not form a fuzzy topology. Now, fuzzy open sets are fuzzy Pister pre-open, but not conversely follows from example this. Now we introduce a new type of fuzzy neighborhood of a fuzzy point, the class of which is strictly larger than that of fuzzy neighborhood. Set A is called fuzzy Pister pre-neighborhood of a fuzzy point X alpha if there is a fuzzy Pister pre-open set U containing X alpha and contained in A. If A is itself fuzzy Pister pre-open, then A is called fuzzy Pister pre-open neighborhood of X alpha. Next definition, a fuzzy set A is called fuzzy Pister pre-quasi neighborhood of a fuzzy point X alpha if there is a fuzzy Pister pre-open set U coincident with X alpha and contained in A. If in addition A is fuzzy Pister pre-open, then A is called fuzzy Pister pre-open Q neighborhood of X alpha. Now, since fuzzy open set is fuzzy Pister pre-open, so we can conclude that fuzzy neighborhood is fuzzy Pister pre-neighborhood of a fuzzy point X alpha. Fuzzy Q neighborhood of a fuzzy point X alpha is also fuzzy Pister pre-Q neighborhood of X alpha, but converses of these two are not necessarily true. Follow from the next two examples, example 3.11 and 3.12. Next, for any fuzzy set A, X alpha belongs to Pister pre-closure A if and only if every fuzzy Pister pre-open Q neighborhood U of X alpha U is Q coincident with A. It is also shown that Pister pre-closure is an idempotent operator. Now we come to the next section. A function f x to y is said to be fuzzy Pister pre-continuous if for each fuzzy point X alpha in X and every fuzzy neighborhood V of f x alpha in Y, closure of f inverse V is a fuzzy pre-neighborhood of X alpha in X. Now we characterize this function. For a function f x to y, f is fuzzy Pister pre-continuous if and only for all fuzzy open set B of y, f inverse B less than equal to pre-interior closure f inverse B. If and only for all fuzzy open set A in X, f of pre-closure A less than equal to closure F A. So from the last theorem, we can conclude that inverse image under Pister pre-continuous function of any fuzzy open set is fuzzy Pister pre-open. Another characterization. For a function f x to y, if f is fuzzy Pister pre-continuous, if and only if for all fuzzy open set B of y, f inverse B less than equal to pre-interior closure f inverse B, if and only if for each fuzzy point X alpha in X and each fuzzy open neighborhood V of f x alpha in Y, there exists a fuzzy Pister pre-open set U containing X alpha such that f of U less than equal to V. If and only for all fuzzy closed sets F in Y, f inverse F is fuzzy Pister pre-closed. If and only for each fuzzy point X alpha in X, the inverse image under F of every fuzzy neighborhood of Fx alpha is a fuzzy Pister pre-neighborhood of X alpha in X. If and only for all fuzzy set A in X, F of P star P closure A less than equal to closure FA. If and only for all for the set B in Y, P star P closure F inverse B less than equal to F inverse closure B. If and only for all for the set B in Y, F inverse interior B less than equal to P star P interior F inverse V. If and only if for every basic open fuzzy set V in Y, F inverse V is P fuzzy P star P open set in X. Next characterization, function of x to y is fuzzy P star P continuous if and only if for each fuzzy point x alpha in X and each fuzzy open Q neighborhood V of fx alpha in Y, there exists a fuzzy P star P Q neighborhood W of X such that f of W less than equal to V. So we have a note, the inverse image of fuzzy pre-open set under fuzzy P star P continuous function need not be shown. Need not be fuzzy P star P open set follows from this example, example 4.7. Now, from the definition, we can easily say that composition of two fuzzy P star pre-continuous functions need not be so, follows from this example. Now, let zxy be three FTSs. For any functions f1, z2x and f2, z2y, if f z2x cross y defined by fx equal to f1x, f2x, for all x belongs to z, is fuzzy P star pre-continuous function, then so are f1, f2. Next theorem, let f x to y be a function from an FTS x to an FTS y and g x to x cross y be the graph function of f. If g is fuzzy P star pre-continuous, then so is f. Next, to recall the definition, a function of x to y is called fuzzy continuous if the inverse image of every fuzzy open set is fuzzy open. So it is clear from definitions that fuzzy continuous function is fuzzy P star pre-continuous, but not conversely follows for example this. Now we come to next section. In this section, we first introduce what is called fuzzy P star irresolute function. A function of x to y is called fuzzy P star irresolute if the inverse image of every fuzzy P star pre-open set in y is fuzzy P star pre-open in x. Now we characterize this function. Function fx to y is fuzzy P star irresolute if and only if for each fuzzy point x alpha in x and each fuzzy P star pre-open neighborhood v of fx alpha in y, there exists a fuzzy P star pre-open neighborhood u of x alpha in x less and f of u less than equal to v. If and only for all fuzzy P star P closed set, inverse image of this set is also fuzzy P star P closed in x. If and only for each fuzzy point x alpha in x, the inverse image under f of every fuzzy P star P open neighborhood of fx alpha is a fuzzy P star P open neighborhood of x alpha in x. If and only for all fuzzy set A in x, f of P star P closure A less than equal to P star P closure fa. If and only for all fuzzy set B in y, P star P closure f inverse B less than equal to f inverse P star P closure B. If and only for all for the set B in y, f inverse P star P interior B less than equal to P star P interior f inverse B. Now, another characterization. Function of x to y is fuzzy P star P irresolute if and only for each fuzzy point x alpha in x and corresponding to any fuzzy P star P open Q neighborhood v of fx alpha in y. There is a fuzzy P star P open Q neighborhood w of x alpha in x such that f of w less than equal to v. And it is clear from definition that composition of two fuzzy P star P irresolute functions is also shown. Now, if f x to y is fuzzy P star P irresolute and g y to z is fuzzy pre-continuous or fuzzy continuous, then g compose f x to z is fuzzy P star pre-continuous. And it is a remark that every fuzzy P star pre-irresolute function is fuzzy P star pre-continuous, but not conversely follows from this example. Next, we recall some definitions. A function of x to y is called fuzzy pre-irresolute if the inverse image of fuzzy pre-open set is fuzzy pre-open. Next, a function of x to y is called fuzzy open function if image of fuzzy open set is fuzzy open. Using these two definitions, we have the theorem. If f x to y is fuzzy open and fuzzy pre-irresolute function, then it is fuzzy P star pre-irresolute function. Last section. In this section, we introduce our desired regular space, and FTS x tau is called fuzzy P star pre-regular space if for each fuzzy P star pre-closed set f in x and each fuzzy point x alpha in x not in if there exists a fuzzy open set u in x and a fuzzy P star P open set v in x such that x alpha q coincident with u, f less than equal to v, and u is not q coincident with v. Now we characterize this space. X is fuzzy P star P regular if and only for each fuzzy point x alpha in x and each fuzzy P star P open set u in x q coincident with x alpha, there exists a fuzzy open set v such that x alpha q coincident with v less than equal to P star P closure v less than equal to u. If and only for each fuzzy P star P closed set f, this is equal to intersection of closure v such that f less than equal to v if v is fuzzy P star P open in x. if and only if for each fuzzy set G in X and each fuzzy pista P open set U in X such that G Q coincident with U, then X is a fuzzy open set V in X such that G is Q coincident with V and pista P closure V less than equal to U. So from this last theorem, we conclude that in fuzzy pista P regular space, fuzzy pista P closed set coincide with fuzzy closed set. That is, fuzzy pista P open set coincide with fuzzy open set. So in this space, there is no difference between fuzzy closed set and fuzzy pista P closed set. Now, next theorem. If f(x) to y is fuzzy pista P continuous function where y is fuzzy pista P regular space, then f is fuzzy pista P resolute function. We all know the definition of fuzzy covered, subcovered. We only state here the fuzzy almost compact space. And FTS X tau is called fuzzy almost compact if every fuzzy open cover has a finite proximate subcover. This is given by D.I. Concilio Garda. Now we have the last result. If f(x) to y is a fuzzy pista P continuous surjective function where x is fuzzy pista P regular and almost compact space, then y is fuzzy almost compact space. These are the references. Thank you.
Thank you, Anjana Bhattacharya. So, is there any question from the audience? Okay, once again, thank you for your nice presentation. Now we have one more presenter, Suchitra Vishwas. Are you here?
Yes, sir.
Okay. So she's going to present the paper entitled A Generalization of Anders Phi Graph. So Suchitra, you may please start.
Okay, thank you. Is the screen visible?
Yes, it is.
Okay. Hello everyone, I am Sucharita Vishwas from Presidency University, Kolkata. Upcoming few more minutes, we will discuss about a family of graphs called generalized Anders Phi graph. We start with the introduction and the definitions, and then we will prove some structural properties and the automorphism group of this family. Bela Anders Phi introduced a family of graphs called Anders Phi graph, and it is denoted by end k. It is a Cayley graph on Zn, that is, it is a circulant graph where n is equals to 3k minus 1 and k belongs to the natural number. As it is a Cayley graph, so it must have a generating set S which contains the elements 1, 4 to n minus 1. Here is a picture of Anders Phi graph where we take k is equals to 4. So basically, we generalize this family of graphs and introduce a new family of graphs called generalized Anders Phi graph. Unlike Anders Phi graph, the generalized Anders Phi graph GATK has two parameters, t and k. It is also a Cayley graph on Zn, where n is equals to t into k minus 1 plus 2, where the generating set S is containing the elements 1, t plus 1 to n minus 1. So clearly, if we take t is equals to 3, we have our actual Anders Phi graph. As it is a Cayley graph on Zn, that is, it is a circulant graph with the generating set of size k, hence it is k regular. And as we all know that the Cayley graph are always vertex transitive, hence it is a vertex transitive graph. Now, girth of a graph means the length of the smallest cycle containing in that graph. We prove that GATK has girth 4, hence it is triangle free. Otherwise, if it contains any triangle, then the girth must be equals to 3. Now, as our natural convention, the diameter of any graph is the maximum distance between any two vertices. We prove that the diameter of GATK is the ceiling of T plus 1 by 2. Next, a graph is called bipartite graph if we can partition the whole vertex set into two independent sets. Independent set means if we consider any two vertices from that set, then there will be no edge between them. We will prove that GATK is bipartite only if T is even. So let's start with T is even. Hence, N is even as we have defined. Now consider A and B as follows. From the adjacency condition, we can easily check that A and B are independent set and of course they are disjoint, and A union B gives us the whole vertex set. Hence, it is a bipartite graph. Now, when T is odd, we have a cycle 0, 1 to T minus 1 of length T plus 2. That is, GATK contains an odd cycle. Hence, it cannot be a bipartite graph, and this completes our proof. An easy corollary can be followed from the theorem. That is, if we take T is equals to 2, then the GATK is complete bipartite graph with equal partite set of size k. Now, complete bipartite graph means every vertex of set A is adjacent to every vertex of set B. Next, the chromatic number of a graph is the least number of color so that we can color every vertex such a manner any two adjacent vertices can't get the same color. We will prove that the chromatic number of GATK is equals to 2 when T is even and equals to 3 in any other cases. So, when T is even, we have already shown that GATK is bipartite. Hence, we can give a color to the set A and another color to the set B. Hence, the chromatic number is equals to 2. Now, when T is odd, it is not bipartite. So, the chromatic number must be greater or equals to 3. Hence, if we can find 3 independent set, then we are done. So, for the odd T, let us consider this ABC as follows. From the adjacency condition, we can easily check that A, B, C are independent and of course they are disjoint, and A union B union C gives us the whole vertex set V. Hence, the chromatic number is equals to 3. At last, we have the automorphism group of GATK. Now, an bijective map phi from the vertex set V to V is called an automorphism of that graph if it sends the adjacent vertices to the adjacent vertices and non-adjacent vertices to non-adjacent vertices. The set of all automorphisms of a graph forms a group under mapping composition as we have in our group theory. We denote the automorphism group of GATK by ATK. So, at first consider T is equals to 2. Hence, N is equals to 2K. As we have seen that in this case, GATK is complete bipartite graph with the partite set of size K. Hence, the whole automorphism group is isomorphic to SK cross Z2. Please note that the Z2 comes from the map where we can send the every vertex of A to B and every vertex of B to A. Next, we consider when K is equals to 2. In this case, GATK is isomorphic to Cn, that is the cycle of length n. Hence, the automorphism group of Cn must be generated by the rotation map and the flip map. That is, we can get the group is exactly isomorphic to the dihedral group Dn. Now, for the remaining cases, when we have T and K both are greater equals to 3. In this case, of course, GATK is not isomorphic to Cn, that is, it is not a cycle of length n, but still we can prove that the whole automorphism group is generated by the flip map phi 1 and the rotation map and the flip map tau and the rotation map phi 1. Hence, again, we have our automorphism group is exactly isomorphic to Dn. The paper generally Sanders phi graphs was published in this journal. And thank you. This is the end of my talk.
So is there any question from the audience? Okay, then thanks to Sucharita Viswas for this nice presentation.
Thank you.
And so we are at the end of this session, or sir, please, the session is handed over to you.
Thank you, Sumit, for chairing this wonderful session. All the presentations are really good, and most importantly, the timing management was great. So initially we were running out of time, but now it's perfectly okay. So thanks to Dr. Shumit Kumar Debnath for this wonderful chairing, this wonderful event that you made, and all the speakers that were present here for their wonderful lectures and presentations. So with that, that's the end of this technical session 3A. The technical session 3B is just now over, so I guess the participants over there will also join here. But most importantly, due to the scarcity of the online participants, what we did, we actually shared the link over internet for YouTube link. So most of the participants are actually viewing this event through YouTube. And for the last day, we had more than 550 views of our conference first day. So I'm sure that today also we'll have similar views. So many participants are there, and we are also watching if anybody of the viewers from YouTube would have any question. If they would have any question, we will certainly convey this to the speaker over there. But YouTube is actually running, there is a lag. So it's maybe a 2 minutes or 3 minutes lag. So, but if we have any questions, certainly we will raise it to the corresponding sessions. The volunteers are already there who are taking care of all those things. Okay, so thank you, Sumit, once again, and all the speakers again for this. Now may I directly go to the next technical session 4, and I'm sure that whether Professor Shengupta is there. Let me check. I think he might be joining in a few minutes. So if you would like to check your slides, you can do this by presenting yourself the screen so that we can start on time at 6 p.m. of Indian Standard Time. So we have some time. So here, Eric will be the first speaker. Dietrich, I can see him. Barry Arnold is not yet present, I guess. Not yet, but since it's quite early in US, so maybe. So I can see Indranil. Nice to meet you again online, though online. Yes, Eric is presenting his slide. Great. So, yes, so we can see your screen. Great. It's doing well. Let's see if, yes, so maybe, and Professor Rosen, would you like to also check your screen as well? Professor Dietrich von Rosen, would you like to also check if the slides?
Yeah, I can try.
Yes.
Off
So,
the air.
Professor Trail, could you please just off the? Could you please stop sharing your screen? Then Professor Dietrich may also try if it works, because we have 10 minutes around time on hand. Yes, this just stop sharing. If you just minimize that, please minimize the screen of the slide. Yes, then you will find the meeting link. Great. So if you just stop presenting, then that will. Please click on the meeting link. Not that one. Not that one. That will end up your meeting. Just click on the slide. Yes, you click on that. Yeah. You may, yes, and then stop sharing. Yes. Can you please just stop presenting? You click on that. Stop presenting. Not this one. Not that one. The red portion will make you out of the meeting. Yes. So maybe. Yeah. Now click on that. Yeah. Great. So Professor von Rosen, would you like to share your screen, please? Yes, we can see your screen. Great. Thank you.
Okay.
Yeah.
That's good. Then I should learn to check out also.
Yes. You just, yeah. Great. It's done. Just.
Good. Then I'm not so nervous anymore.
Oh, yes, I can see you. Yeah. Thank you. So, yes, so the speakers and as well as Professor Shengupta is amongst us. So we can start now. Maybe 4 minutes. 4 minutes are there still with us. And Indranil, would you like to check your screen as well?
Abhishek, you have all the speakers?
Yes, at least 3 speakers are already there. Professor
We need the
Sujit,
first speaker, and he's here. I
yeah,
can
he
see
is here.
that
He
the
is
trail
here.
is here already. So no problem, we can start.
Yes.
Okay.
So if you would like, you can start. And
No, we'll wait till the time, okay? Because
yes,
there may be other people who'd like to listen to the talks.
Yes.
So we should start in time.
Yeah.
We don't want him to start early and they'll miss his opening remarks.
Yes.
We'll wait for everybody, okay? We'll start dot on time.
Yeah.
I was asking, so Barry is here, and then of course Dietrich and Sujit and Indonil, all 5.
So can you see Barry over here?
No, that's why I was asking you. I could not see.
No,
I'm
no,
just
no,
trying
yes,
to open up the list. 10 others.
Yeah, Barry and Sujit not yet joined, so they
No,
may join.
I don't see
Yesterday,
the
Professor
other ones. 10
joined.
others.
Yeah.
Who are the 10 others?
Yeah, so maybe it's too early to them.
Yeah, let's see. Amrish, Panda, Abhishek, Adi, Jetish is here, of course. Indranil is here. We have the 3 speakers, and Shujit I don't see yet. I don't see Shujit and Barry yet.
Yes, so
maybe they'll come in as they start. Okay.
Yeah, they will join. Yeah. So maybe I just hand it over to you.
So we'll start at 6 o'clock, right on time.
Yeah.
So let's wait. They may be wanting to listen to Dr. Trail's talk also from the beginning.
Yeah.
We'll start on time. Okay, Abhishek?
Okay. Yeah. So the last session actually ended up with just on time. It's on 5:50. So we had 5 minutes, and all the speakers, they have already tested their screens previously. So they are now very expert on sharing their screens. So it's very easy, convenient for them to share the screens now. So they don't need any time.
Abhishek and Professor Trail, I'd like Professor Trail to give a self-introduction, if he doesn't mind, because I have seen his work. I mean, I heard his talk also. I can give a brief intro, but it may be better if he, without being modest, he can say something about himself so that we can learn more about him. Is that okay with you, Professor Trail? Your mic has to be unmuted. I think it is muted. Your mic is muted. We can't hear you.
Now I think I'm.
Now I can hear you. Yeah,
Yes,
now
yes,
I can hear.
yes.
So we'd request you to, without being modest again, to say some words about you so that we can all.
Well, I am a retired professor of general
Not
medicine.
right now. When we start the session.
I see. Yes.
In the beginning,
Okay.
I'll request you to introduce
Yes.
yourself. Okay.
Thank you.
Barry, Shujit, all other four I know pretty well.
Yes.
So,
Yes. Yes.
I don't need anything, but from you, I think we'll appreciate your introduction.
Yes. Thank you.
So how was the session, Abhishek? All the speakers, there's no problem with the connection. Internet was okay?
Yes, internet was perfectly okay, and we did have around 28 presentations. As usual, we had only one absentee.
Wow.
It's a great, and
that is impressive. That is impressive. Okay.
Yeah, and all the speakers actually they just spoke within the time frame, and it was great.
Okay.
So thanks to the chair as well, because they have maintained it nicely.
Okay, so I take that as a hint. So I'll try to abide by that. Okay.
Men det är bättre, jag kan gå in själv och titta.
Maybe the Professor Trail can, after I just introduce this session, then Professor Trail can share the screen with you. I guess, Abhishek, you can now put us on the screen.
Yes. Yeah, so it's now the time. So today now we are going to start the technical session 4. It's a special session mostly on statistics as well as theoretical physics-based topics are there. So here we have 5 distinguished speakers. So without any further delay, may I now request our Honorable Chair, Professor Dr. Ashish Sengupta. He is quite eminent, and I'm sure that you all know about him. He's a very good speaker, so this time we are not having him as a speaker, but of course we won't miss the opportunity to make him as a session chair. So without any further delay, let's welcome Professor Sengupta to please chair this session.
Thank you, Abhishek. Thank you very much for giving me this opportunity. I would definitely not like to miss this session, even though I'm not the speaker, which I'm enjoying. I just finished giving my lectures just a couple of days back, and then there's upcoming 2 more conferences I have to speak there. So I welcome the relief, and I thank you for giving me the opportunity to chair this session. So we have today a very good and eminent speakers. There are 5 speakers. So 2.5 hours, 150 minutes. So 30 minutes for each speaker. So it depends on you whether you want leave some time to have questions or you want to just give your talk. So plan on that. I will suggest, again, I say it's up to you. Maybe you can give your talk for 26 minutes and leave 4 minutes for a couple of quick questions. Okay. So with that, we'd like to start our session, and our first speaker today is Professor Erik Schell from University of Linköping, Sweden, and his title is Self-Assembled Nanostructure of Atoms and Molecules with Examples of Various Organic Compounds, including the proteinogenic amino acids and DNA. So Professor Erik Schell, yesterday during the inaugural session, gave us a very bird's eye view of his expedition with IMBIC, if I may say so. He has been with us for quite a long time. We have all enjoyed his talks, and also we are familiar somewhat with his work also, though he works in physics. But we welcome him, Professor Trell, and I invite you to say a few words about yourself, to introduce yourself to the audience, please. Professor Trell, over to you.
Yes, thank you very much. And I also try to get my presentation on the screen now. So I have it here. We shall see. I put it down here. 25. Yes, here I have it. And then we can take a little other action of it. We shall see. Now I shall see. Now I shall see if I can. Fantastic.
Yes. Fantastic.
I'm so relieved.
Congratulations. Yeah, you can see the entire screen. Thank you.
Yes. Well, again, I repeat, it's such a fantastic event, these conferences. And as I mentioned yesterday, I am a retired professor of internal and general medicine. And quite a few years now I have been that, but I still go on as a general practitioner part-time up in a community in Värmland, which is mid-Sweden, which is a kind of concentrate of Sweden, you would say, nature and temperature-wise. And Avishek and family has visited us in Värmland and can witness about the landscape and all, and how it feeds a lot of thinkings and reflections on nature and such. So I would say my interest in the natural sciences is in a way inborn. And it so happened that I had this opportunity to combine it with mathematics, which was also an old fancy of mine, and under the guidance of Professor Mahima Adhikari, and more also Avishek, who was quite young when I met him first, has evolved to the present speech, if one may conclude it. So with that, I could start perhaps my speak, if it's okay with you.
Professor Schell, you can go ahead. Please start your talk.
Thank you very much. Well, you mentioned the title of it, and it's about, you can say, polymer. It's about having a structure appreciation of matter, and that is, of course, in a way, self-evident, but it goes after the lines of Marius Sophus Lee, and he made this doctoral presentation in Norway in the Norwegian language, which no one understands except Scandinavians, but Swedes understand it. So after having tried to learn about Lie geometry and Lie algebra and Lie groups by the textbooks of the 20th century, I decided to go to the university library in Oslo and get it. And I then also made an English translation of it, which is available on the net, by the way. Anyhow, he invented, you could say, the infinitesimal transformation groups. And that was before actually his work with the continuous groups, which he's famous for, but he made a lot of other things before that. And one of the things he made was to resolve the imaginaries. So everything he does is in real space from the start. So one can go on quite directly to what actually he does. He made one of the greatest transformations, namely between the Plücker straight geometry to the spherical geometry. And this is a kind of split vision of our world. Is it straight or is it round? Or is it both? Anyhow, his phase transition was between the inner surface of maximally extended Euclidean Plücker space and the outer surface of the maximally contracted sphere, you could say. And everything that happens in the interstice between these maximal forms. So there is a tension, you could say. There is really something that attracts here. And you could say perhaps it's the dark mass or its equivalent. And the methods and so forth are familiar, so I don't rush upon these. But what we end up with is infinitesimal generators at the identity of the R3 times SO3 configuration space. It's a double, and you can say we can figure it out in this drawing here. And I think it's also self-explaining, so I'll rush on. But we feel that doing so, we have a network instead of a flat diagram, and we can make various kinds of lattices here, and they are mutually tangent to each other, which illustrates it's a tangent space occurrence. And the years before, let's say the first 15 years, were about the internal transformations, those of the elementary particles. Looking upon this figure here as a kind of the nucleon, it can transform inwards by the elementary particle transformations and so forth and so on. And thus I made illustrations of them. And the other thing is it can also act outward. And now going to the periodic table and the atoms, it's the outward transformations I deal with. So to illustrate just the inwards, some of the transformations that were made are shown here, and this is the octet, and they came out as ellipsoids and very nicely reproducing the observed sigma and delta and lambda particle transformation. But the other way is out in tangent space, as it were, and tangent space is tangent to the Lie group, then a manifold of SO3 times. But technicalities I will avoid now, so I instead show graphically how it works. If you have the kind of nucleon cell here, and you take the vectors of that and you connect them, you get a lattice, and that lattice returns to itself non-overcrossingly. And that's a problem, because then you can not do anything else than come back to yourself. And it's very good if you can extend this coming back to yourself by splitting the kind of dividing the figure of 8 kind of situation, or the not situation that you have. Because what is the effect of a transition between the cubic space, which we always realize is a non-overcrossing network, but you can't draw it non-overcrossingly, and the space frame, the spherical network, which is octahedron, tetrahedron truss. And that is possible to draw non-overcrossingly. But how? How to do that simultaneously and how to find your way? Because if you just go out like randomly, you will jam immediately. And so this can be solved by dividing both the R3 part and the SO3 part in terms of single line, which when meeting resistance will turn and then combine to the ready network. And this would be the frame space then. Likewise, the kind of wave space which could be divided in one outgoing and one returning, and thus combine to the kind of system that I'm operating with, that can be combined with an outer frame space of R3 and an inner wave space of SO3, and slightly higher weight, of course, of the frame space, which would be the neutron. And it can go separately then too with the neutron here, or it can go separately here with a protium actually as a ground. And it still is so. If it's halved, it will return to the origin, even if the cause is divided. So what we create here is a frame space, is an octahedron, tetrahedron truss, and the nucleon is the node of the construction. I rush because so it's a kind of curve here that would fill the cube, and there is the Peano-Hilbert curve, but this is fractal and not differential. So if you should do it differentially, you need to, so to say, find a way of packing the space so that you can introduce the orthogonal, the SO3 curvature into the Euclidean space. And you can do this by packing space in this way. And then you end up with a kind of Bohr Aufbau. So this is actually a Bohr Aufbau of, you see this 2, 8, 18, 32, 32, 32, 18, 18, 2. And then, of course, one wonders, how can it be packed so? And this is a kind of remaining, but I think there are some Fourier transforms and other algebraic curves that could be illustrated so. But now we have half of the solution to pave space, so to say, to go on in a way that doesn't cross or jam. And the problem is we have a flat bottom, but we need a flat roof too, and that will be self-induced in lack of any explanation. But in anyhow, now we have a cubical kind of procedure. But we would find we have not so much help by this one because it will jam itself. It can't find place for the last digits. So we must have another because this will be not constructive. It can be used in some situations, but it's so we need a tangential solution when two of these modules, as I call them, they clash tangentially, and then we have a triangular kind of unit which then corresponds to, because being loaded both with the space and with the wave part, and that would be deuterium, as I will call hydrogen in the continuation, and then it can be so to say skewed to helium. I go through this system now a bit this is only a repetition of the system, which would be perhaps clearer now. You see, if you crush this by some collision or so, then the wall elements will go straight into neutrinos, or it will be zigzag like gammas. So the system has a kind of consistency also in that way, that it can be destroyed into those collision elements. Anyhow, the way of building up the system would be to illustrate it here in the deuterium from if you have a neutron and it squeezes, it can combine to one helium-3, which is one hydrogen-3, which of course, but it can also, if you have the loaded component, be 2 helium-3, and if it's full squeezed, it will be 2 helium-4. I go through this now with some other things, because then you can add these blocks and you get 3 lithium-6, 3 lithium-5, 2 helium-5, 4 beryllium-8, and so forth and so on. And you see that you can stash these. So these are space filling. And those yield very complicated when you get more and more. So you must find a way of duplicating them and making them simpler. And that I call duplo elements, because then you idealize and simplify these to square forms again. And these are already a bit out of perspective, because they should be actually the root of 2 in the but they are nice to deal with. And I ask you to see this. You can see the binding site: lithium-1, beryllium-2, boron-3, carbon-4. So carbon is the real spindle of the net, you can say. It's extremely constructive. And then you have nitrogen and oxygen. And then you have actually all the elements of life. This is organic chemistries. With hydrogen, with carbon, with nitrogen, with oxygen, you build life. So the only elements you need to deal with would be these. And then there will be some trace elements in the rare cases, as will be illustrated. But basically, all organic chemistry is built by these building blocks, which are very, very much, you could say, simplified here. But anyhow, the scheme goes on with filling the remaining corners in the so it goes to argon, and now it's fully satisfied. So it's got a square form altogether, and then you can just stash margins after margins, and you can also see that you can find combination between the alkalis and the halogens, and you end up in the 7th marginal, you end up with organesson, and that is very symmetric and very perfect in a way, because it shows also the meaning of neutron excess. You need these neutron excess to make an ideal kind of element. Anyhow, I come back to the situation here, and I don't know if you recall that how do you get this over because an atom, and these modules, as I call them, they are of reduced space, and how shall we make them bigger? Because an atom is about 10,000 times bigger than the elementary particle size. And I only show them here in terms of carbon, nitrogen, oxygen, and hydrogen, that you have to increase first surface-wise over the plane. And then when a plane is ready, you have this here, and it comes back after a very long time to the corner, and then it goes up, and then it pays next, and then it pays up. And that is a very, very long and big increase. Anyhow, in that case, you find that it comes out as an atom, as a crystal. And that is a mystery of atoms. How come that waves, if there are waves, come out as crystals, and that these crystals have such distinct forms? Because they always come out as solids. And this is actually the collection of them that come out as solids. But anyhow, this would be by this way, they do pack as crystals from the start. And I return now to our ground elements, the carbon. This is its motif, if you so say. And we have nitrogen, and that's its motif. And oxygen is the motif. And then, if it's so that with hydrogen too, which would be just this square block, how come that they suffice for the chemical elements? So we try this with hydrogen, carbon, nitrogen, oxygen, and having them by the previous method increased in size. And they come out as blocks, as I said, but they can also be, so these would be the blocks, but these would be the plates if you make a jigsaw puzzle of it, for instance. And also the kind of depth of this block, the number of layers of the increase to full crystals would mean that if you have only a limited number of layers for some temperature reasons, that could be gaseous. If you have more, they will be fluid. If they have full atomic size, they might be solid. So that goes so far. And we have isomeric forms. But I think now it's time to go back and see what we can do. If you take carbon, for instance, if you pack them together, and we see here a photo of how actually a graphite surface looks like. It's a kind of, and you see also the way of drawing it by this ball and stick method. And that will be then more like empty space combined. Anyhow, it's evident that they can couple them into various kinds of conformations here. And here, instance, are the fullerenes, for instance. And then you see there would be some empty blocks here between. How are they filled? Yes, they are filled by water or something else. So it's all coming together, but they are separate structures then are directly. And we go just through the basic elements, the methane, the carbons, hydrocarbons, and we take the various molecular combinations. Water would be like this. This we already have as kind of space filling diagrams, but here they come out as a kind of squares, and we have also the ammonia and methylamine, and you see that they are space packing. I rush through this to come to here we have cyanide, hydrogen cyanide, hydrogen fluoride, and so forth and so on. And they are all space packing and can be thus distributed together. And we have carbon monoxide, carbon dioxide. We have also the lithium, beryllium, boron, hydrides, and oxygen. So one gets a bit astonished. But on the other hand, if it is so it looks, you shouldn't be astonished. So it's a kind of split reaction to these findings. Anyhow, if you go on with molecular structure, ethanol, for instance, it's combined by you have the number of elements, and then you have how they can be combined. They could be combined in various ways. And they would always be linkable to each other because they share a kind of profile, which is both lengthwise and sidewise. And of course, they are also stashable over each other because they are flat. roof and flat bottoms. And if you think further about this, this would be the solution to how can come that the elements are preserved, as it were, even in the turmoil of the center of the world. Yes, because they are layering a top of each other, so they will defend their territory unless being squeezed out of it. So we take another ethanol, for instance, and how that can be combined. It's made of these, and we take ethanol, the liquor. It's just 3 elements, and these are the atoms involved. And the hydrogens you already see, they are very strategic because they occupy various places here. And in fact, there is one CH3, and it's one CH2, and one hydrocarbon that makes liquor. But then there are a lot of tastes, of course. Glucose, for instance. Now we have 3 main sugars, glucose, fructose, and galactose, and they all rest upon this various distribution of their 6 carbons, 12 hydrogens, and 6 oxygens. And here we have 6 CH2 and 6 O, making this kind of, and here we have instead 6 carbohydrates and 6 hydro. And then we have galactose, which is 6 CH and 1 oxygen and 6 hydrogens. So here the hydrogens act by themselves. This is just, I wouldn't claim that it looks like it, but it looks like this when you apply these elements. We have the hydrocarbons, and these are ethane, propane, butane, pentane, and they can be many times magnified, I mean, or multiplied. So you have very long chains of these, and they could be also made with another. But I just go through, and coming to more complex molecules, we now show again the present space filling, which are space filling by their wave. And this is a ball and stick, and that's one wonders what's between these and so to say, and what are sticks made of. But anyhow, if you take and combine 27 carbon and 46 hydrogen and 1 oxygen in this way, you get the cholesterol in a way that is not space filling, but it's layerable, because cholesterol is the way they layer in your blood vessels, but they are hooked up by various phospholipids and so on. So you see they have a kind of anchorage in each end, and there we can hook in. And we already have the use of these contours, these profiles.
So is it you have 2 minutes? So is it
Yes.
you have 2 minutes? 2 minutes. 2 more minutes.
2 minutes.
Yeah.
Yes. I now come to the proteogenic amino acids, and this is a very big mystery. How come that we can fill space by these simple modules? And I just show you very roughly how it can be done, because we put these in an obliged position, and then we can make them link and form rings and so forth and so on, which is actually how proteins are made. So this will be just, you can always see the primary structure, and you can see how they can be asparagine, I suppose, and so on, asparagine. And this is aspartic acid, this is cysteine, here comes sulfur into the glutamic acid, and we have glutamine, and we have glycine, we have histidine, we have isoleucine, and we have a bit of things here. And now I just say that this slide series ends with pyrimidine, which is not amino acid, but it comes to the DNA, which is the kind of Kalman here, which is made of a phosphate deoxyribose backbone and bridges by adenine, thymine, cytosine, guanine. So this is how it looks in the present. But if we take out this cytosine, for instance, and build upon pyrimidine, we see that it's an obliged things. And I show here that there are 5 hydrogens missing here. And if we put them in the end, we get this kind of configuration. We can also see that we can layer them like this. And we take the sign with thymine and show them with the end here. And we take the same with adenine and show them by the ends here. And we take the same with guanine and we show them by the ends here. And the peripheral hydrogens are very strategic. And now we can also make the phosphate deoxyribose backbone here, up here. This would be the phosphate and this would be the C5. So this would couple to this kind of backbone. And you can see that you can link in cytosine, click in, as it were, cytosine and other things. So you would come to this kind of model, guanine, thymine, adenine, cytosine, for instance. They would be possible to trace like this. And you see there are the various brands. And this is quite interesting because if you make this guanine, cytosine in this order and you just revolve them in the chromosome structure, you get the inverse of this. And if you just approximate them, they will close. And this is the meaning of the various lengths of these arms. So we actually have a kind of alternative explanation of this deoxyphosphate deoxy backbone and these links that will close in that position. And we can just end up by this figure and see that they are only just the last 4 of the immensely long chromosome arm, which these are 4 base pairs. But you can continue this model endlessly because they will click in with each other and just showing the immense structures. But these models do fit in, and I was able perhaps to give some glimpses, and there are in the manuscript which I have written, and I tack för er uppmärksamhet, which is thank you for your attention. Thank you.
Thank you very much, Professor Trail. So you finished it in time, in spite of a talk which would need a lot of time. You gave us lots of information, very interesting. We have a time for just one quick question. Anyone in the audience, you want to have a question for Professor Trail? You can raise your hand. Okay. I think they'll probably wait to look at your papers that you told us about. It was a very, very interesting talk. Thank you so very much. For the sake of time, we need to move on to the next speaker.
Yes.
So our next speaker, thank you again, Professor Trail. You can now unshare your talk presentation.
Yes. Yes.
Our next speaker is Professor Dietrich van Rosen from the Swedish University of Agricultural Sciences, Sweden. He's going to talk about applying ridge regression. Professor van Rosen is very well known to us. He has been a regular speaker in this conference and he has visited India several times. I met him, in fact, many years back in some other conference. His research areas are quite varied and profound. He is very well known for his work in growth curve analysis. In fact, a couple of my PhD students have worked on those concepts with using some of his work. And also, he is doing some work on bilinear regression analysis. It's a new area. He has already published one book, Advanced Multivariate Statistics with Matrices, and this book on bilinear regression analysis is upcoming next year. If you want to see something before that, you can look at his paper in Shankhya. He has a nice paper on bilinear regression analysis. As I said, he's a visiting professor in mathematical statistics at Linköping University, and also professor in statistics at Swedish University of Agricultural Sciences at the Department of Energy and Technology. He has published more than 100 papers and 16 PhD students, and he has published very deep and also wide in a wide areas of statistics. I welcome Professor von Rosen to give his talk today. Over to you, Professor von Rosen.
Yeah, thank you very much for a very nice introduction and great words. I don't know if I don't know what to say about it. I'm flattered, of course, and in fact, I can say a lot of my research traces back to India. It has it's a strong history with India to what I've been doing, and not maybe so much in recent year, but since I'm working classical linear models or multivariate linear models, there are these traces to Professor Rao and many others. So it has always been a pleasure to be in India and to communicate with India. I have been working a lot in Muni Srivastava in Toronto, and I have learned all this collaboration. I've learned a lot. So today I wanted to introduce something which is new to me. So I'm really happy to collaborate with people. So what I'm going to present now are more or less some thoughts. And I don't know how much it's against mainstream, but I still think people haven't thought enough about, you will see, ridge regression, which is a special case, or what we today and often call some kind of penalized estimation. So I started to think about it just because I had to write a manuscript half a year ago. Didn't understand so much in the beginning, or wonder what people, how they have been thinking, and after a while one gets some ideas. And I want to share my ideas with you, and feel free to criticize either after the speech or write to me, because I'm really in a learning process. So I'm going to talk a little bit about ridge regression. The title was a bit wrong. It's not so much about ridge, but it appears now and then. And this is partly of a bigger procedure which we can call penalized estimation. It's big today. It's a whole industry around it with, for example, lasso estimations and group lasso and whatever. My talk will trace back to linear models, least squares estimation. Oh, what happened? Sorry, do you see me more?
Your slide is not moving.
You saw, yeah, I just disappeared on my screen here, but it was my fault when I'm moving the mouse, I think. Okay, so I will talk least squares, then I will take it over to maximum likelihood estimation, and a little bit of multivariate if it's time for it. Okay, background. The idea behind ridge regression. Ridge regression came in the 70s, but it was an older concept. So let's start here with just a classical linear model here. I write that the X is a vector observation. I usually work with column vectors, so I have transpose is a row vector now. There's a mean, and there's a variance, sigma square. And observations are supposed to be uncorrelated here. And C is a known design matrix. And it can be treatment groups, it can be regression with as a usual design matrix. And we can write the model in this way also. And least squares is about fitting or creating an estimate which minimizes this expression here, the square, least squares we're going. And XO is just that instead of a random variable, we have an observation, observed value of the random variable X. And then it's well known that the least squares estimator exists or is given the following way if this inverse exists. Otherwise, we have to look at estimability or linear combinations of the parameter. But just suppose that this inverse exists. Prediction is of this form. You can predict a new observation by making this projection. This is an idempotent matrix, but I will not discuss that part at all. More important is that the dispersion matrix of this estimator here is given here. And what you should observe now that we have a CC transpose inverse. We have it here, we suppose that it exists, and it's also in the estimator and in the variance. But then it was observed that if, for example, this CC transpose is almost singular, the variance will not be, it can be really large. And at the same time, this estimator B can also change pretty much if you just make some kind, or depending on your design. So if you have a bad design that you are almost singular, CC transpose here, then your estimates are poor. And this was observed by several people before. And so then I wanted to improve the thing. And we know that this least squares estimator under the setting I put up, it's a best linear unbiased estimator. So what one first is dropping is unbiasedness. So instead of estimating or using the least squares criteria, one penalized it with another function, another distance in some way. Yes, you take the transpose of the unknown beta with B, and then there's a scalar lambda which has to be determined in some way. So in order to estimate the parameter beta here, we are going to penalize the least squares criteria. And then since this is a differentiable function, we can differentiate it, we get it here, and we solve this equation and we end up in an estimate of this form here. Or not completely, because we still have to estimate the lambda here. And there are many ways of doing it, and usually one has some kind of statistical criteria. I want to have, for example, the smallest or some kind of minimum variance, but minimum mean square error. And then you choose lambda accordingly. But then we lose also, if you have a random lambda here that will replace lambda by its estimate, the distribution of this here is not so clear. But there are approximations and a lot of things. And this estimate is usually called ridge regression estimator. So this was a way to estimate things in some kind of difficult situation where the CC transpose was almost singular. And now we start a little bit different, but we will end up in the same solution. And this is nothing new in principle. Suppose instead that when we want to estimate or do in least squares, that we have some kind of prior information that we know that this beta transpose beta is less or equal to a given t. But we have to assume this t. So there's some prior information. And the first one can then think about if we have this type of model here, because we have a model and we're going to apply least squares to it. And unbiasedness maybe doesn't make sense, because unbiasedness usually is about all possible beta values. So, but now we have restricted beta to belong to some interval, or even we have this kind of limitation or restrictions. And this is, of course, usually if we do statistics, we have some knowledge what beta should be. It cannot be, if you study growth, you don't grow more than, not if humans, a couple of meters per year. We can really restrict the growth, or we know that there is a limitation. Often we know that it's positive also, which also can be used. So this unbiasedness, when we suppose that we should have an estimator which is and a good estimator for all beta, it's maybe not so necessary that it has to be unbiased for all beta. Because when we do this, our statistical inference, if we see some extreme observation, we will remove it or do something else. We just think that this is some gross error. So this is a starting point in some way from my discussion here. So what we have is least squares criteria, and then we have restrictions in our parameter, which we should estimate this least squares criteria over. And what we can observe then is that the usual least squares is a convex function, and beta is also a convex function. And since we have this inequality constraint and we have the convex function, we can use convex optimization tools, and we have this Karosh, Kuhn, Tucker. When I was a student, I just learned about Kuhn, Tucker, but now they have found that the Karosh also had done work in this area. And here's my weak point, that I don't know so much about convex optimization at all. I'm just applying results. So here I'm applying the KKT conditions, and they are given here. And you see there are number equations which should be solved, and they appear, I should have written it before, from the so-called Lagrangian function. So when you differentiate the Lagrangian function, these four conditions appear. And they are not very complicated. This is just to differentiate the square or the square function here also, and then you're going to solve it. And then we have a restriction here. We should see that our solution will satisfy this condition. Lambda is bigger than 0. But then we have a bit special condition which comes due to convexity, because the point is here that if we can find a solution here, we have really found the optimal solution. So the KKT gives necessary and sufficient condition for solving this least squares problem, as mentioned here. So here we can see that there are two ways. That either is lambda 0, but if lambda is 0, we see that we're just back in least squares. If lambda is not 0, then this condition has to be fulfilled, so which solves this equation also. And then we use, if lambda is not 0, lambda will be obtained by considering this BT or B transpose B or beta transpose beta minus T equal to 0. So if we move directly to the solutions here, so as I mentioned, if lambda is 0, then we will just have the usual least squares estimator. Otherwise, if it's not 0, we will have a lambda, which is obtained from, or we can also say that there's another alternative. If we have our observations, our usual standard least squares estimator, if it fulfills this an inequality that beta transpose beta is less or equal to T, Then we have a lambda which is 0, and we have all solutions to this system. So then we have a least square solution. But if it's not the case, then if lambda is larger than, if we look again at these equations, these are the same in somewhere when we had the least squares criteria, where we had penalized the function. We would get exactly the same equation here. And then we can see that this equation, we can move here, see if we end up somewhere. No, I'm too quick, but I thought I had it here somewhere. Yes. Then we have an estimator, which is of this form here. So beta can be written like that here. And if we estimate lambda by solving that equation, then we get an estimator of beta. So then we see that once again we have this type of penalized and the same estimator as we got when we penalized the least squares criteria. So here we have two approaches in some way. One is to think about penalizing the estimation criteria, whereas here now we were putting restrictions on the parameter space. But they give in principle the same result. The difference is in some way that for the second approach we have some t which is supposed to be known and which we have to choose. But I don't think that is so serious. And we will see what if we have this idea of how to say, putting restrictions on the parameter space. Is easier to generalize the inference than we just say we penalize our estimation criteria. So, and also this estimator is usually called this ridge regression estimator, and it's pretty known. And the first to present it was, I don't know how to, if it's Howell or Hurl. He did it in the 70s by together with Kennard, and then he has a pretty nice overview backwards how they developed this. And it turns out that there are some ideas of Hurl in the beginning of 60s, which he included then in a statistical framework. And a nice reference is Gruber's book, where there's a lot about this say ridge regression, but also in general about shrinkage estimators, because this is some kind of special case of shrinkage estimation. So now we want to extend these ideas a bit. When we suppose now that we have a normal distributed random variables, and then it's pretty natural to think about that we should have a likelihood approach where we put some restrictions on the parameter space, not linear restrictions, because linear restrictions we know how to solve. And then one starts to be a bit careful, but the advantage is that one can in some way discuss the sigma, which is the variance parameter, and the beta parameter simultaneously. And then we have one can question, should we look directly on the likelihood? No, it's better to look at the negative log likelihood, because we then have convex functions. So when we have convex functions, we are on the safe side to use these KKT conditions to estimate our parameters. So here we have the negative log likelihood, and we have the restrictions on the parameter, and we should, since we take the negative, we should minimize this function under this condition here. And there are two ways of doing it. The first way I would say, and it gives a bit different, or the first way of doing it, and is just to observe that we can first estimate sigma square, because this function is less or equal to this one here function, which is just a function of beta. And then equality holds if sigma satisfies the usual say maximum likelihood relation. Pointer was flying away. Yes. So we had this will give us a maximum likelihood estimator if we have a usual beta, there is some kind of a least squares estimator. But now we have here the continuation of this negative likelihood when we have replaced the sigma square with the function of beta, and then we still have these restrictions left. So we should now optimize 7 or minimize 7, equation 7 here. But then you see, this is just the logarithm of the function here. So this is our least squares function, which we already have been minimizing. So then we can come up immediately and with the result, which is approximately like this here. So we check first if the usual least squares estimated beta transpose beta is less or larger or equal to t. If it's larger than t, this here, we should refer to KKT conditions. And here are the conditions. Now, of course, this equation which determines lambda is nonlinear and can just be solved iteratively. And here we have the ridge regression with the special choice of lambda here as a function of t. And here we have the variance estimator. And if the least squares estimator of beta transpose satisfies this relation here, then we are back in a usual maximum likelihood estimator. So we have them here, which are identical to the least squares estimators. Here's a bit special here. If you would know that we just have one long, say one treatment group, we just n observations, and these restrictions make it almost deterministic, the whole system. It's just to choose if beta is plus or minus the square root of t, and then we can of course see here also that t has a very strong influence on our estimation, which maybe doesn't make sense then. If we don't make it so large that this beta transpose beta will satisfy it. Okay, another way, or what we can play with now, is if we look here at the same model as before, but now we have restrictions on the parameter space which involve both beta and sigma square. So then one has tried to understand what does it mean that we in principle have restrictions on beta divided by sigma, so some kind of inverse coefficient of variation. And I will not do it because this is like an introduction to the multivariate part. But we can see that if the likelihood, if you look at them, the likelihood here, it's well known that if you look at the inverse of the variance there, then we have a convex function, or the negative likelihood is a convex function also. So then we can go on. So we have estimators here of or parameters of 1 over sigma square. We call it theta. And so we estimate theta. If we have an estimator of theta, then we have an estimator of sigma square. It also indicates in some way that this convexity is maybe not necessary for estimating parameters or finding maximum likelihood estimators. But I don't know today what to do if we have constraints based on inequalities. So anyhow, the KKT conditions give us the differentiate with respect to theta, and the Lagrangian function, we differentiate with respect to beta. We have this set of equations. And then we have, in particular, because we have inequality, this equation here. And then we are back in the situation how with the what to do with the lambda, if we satisfy the condition or not, and we can write up the estimators more or less immediately. So if the condition is satisfied, we get this maximum likelihood, or then see the maximum likelihood estimators. Otherwise, we once again come to such a and say ridge estimator for beta, we have an estimate of sigma, and we have a bit different condition how to estimate the lambda, because sigma square is also involved now, not just t. And then we can try to, we need an algorithm to optimize it, and this I haven't checked how easy, how good this algorithm is, but I expect it to work. Okay.
Professor Von Rosen, please, you have 2 minutes.
Yes, I will round off here. Yes, why I'm doing this, the goal is to later to treat the bilinear or the gross curve models, but first we need a MANOVA model here, and this is given here. And we can do exactly the same, start with a negative log likelihood function, and we put restrictions which look like this here. And of course, there are many objects how we should restrict, but it's important here that we have the sigma inverse, because convexity is not so obvious, or it differs a bit when we have multivariate case. For example, and the determinant doesn't have to be a convex function. The determinant of covariance matrix is not convex, so one has to do a bit. And then we get, but if we look at the log likelihood, we have this kind of conditions here. Then we have the KKT equations, and we can solve them. And then, as before, we end up with some solutions. So these are the usual, can see, here are the, if we have something which doesn't satisfy our restrictions. But of course, it's important to remember that immediately when we have our conditions here satisfy the restriction, that we have classical MLEs which satisfies that is smaller or equal to 2t, then we have found our estimators. So I think this will be the last slide, and we can stop here. What I want you to bear with you is that by putting restrictions on the parameter space, we can obtain similar results than when penalizing, say, the likelihood or least squares criteria. So thank you very much for your attention.
Thank you very much, Professor Von Rosen. We have time for one quick question. Anyone from the audience here? You can raise your hand. Any question for Professor Von Rosen? No? I had a very quick question for you then.
Yes.
You are looking at the normal distribution and of course the log concavity of the likelihood function.
Yeah.
How much, I understand that the log concavity is really needed for the Kuhn-Tucker application, or rather what you called at the Karush-Kuhn-Tucker.
Yeah.
Now, in multivariate distribution, for example, you might come across situations where your normalizing constant is not really so elegant or so nice. So is that a very crucial difficulty for applying a technique?
Well, I didn't follow you. You said...
I'm talking about the normalizing constant that we have there.
Yeah.
And with the likelihood function, the log concavity or minus log is the convexity. So, but there are distributions, for example, where the normalizing constant is not very convenient to use, like the elliptically contoured family, for example. You have the sigma there. So I think your method should go through in those situations. For the elliptically contoured family, what do you think?
I can agree about this normalizing constant. It's in some way gives just trouble here, but I don't know how to handle it today.
Right,
Of course,
but I
it's a
think
function of
that if you have a multivariate elliptically contoured family, your normalizing constant will still come up in the form of the scale matrix.
yes,
So I
it
think
worked. But for the growth curve model, I don't know. No, otherwise, if we have exponential families, then it works everything.
yeah. But the growth curve, you may have some difficulty. Yeah.
Yeah, it's outside already, and even so that if the last time these restrictions I put up that trace sigma minus b beta transpose should be less or equal to t. If I would remove the sigma from there, just look at the trace of b transpose b less or equal to t as in a univariate case, I run into trouble with this process here.
I see. Okay.
And I don't know why it's not so, because one can discuss pretty much here, I think. But,
Yeah, I think we'll have to write and discuss with you. I was not talking about removing sigma. I was rather talking about extending it to multivariate elliptically contoured distributions where sigma is
no.
So
I haven't looked at this elliptical, but I think there will be, everything comes so much more complicated. Also, we know MLEs there and things like that. But if we put these inequality restrictions, and I'm not sure what is available.
Yeah, some general results may be needed. Yes, I agree with you.
It's pretty interesting, I think, that if one starts to extend, because in some way, I think one should avoid this KKT, or one has to understand if there can be other solutions, even if it's not convex.
Right.
And I think in many cases this is too strong, this KKT, or one can just find alternative approaches.
Yeah, some other optimizations or routines may be necessary.
Yeah, because this is, I don't know, convexity is a nice concept if it exists, but if it doesn't exist, it can still be, you can still find unique estimators.
Yeah, I agree. It's through hard computation. You have to go through some hard computations there. Okay,
Yeah, I
thank
don't know.
you.
Yeah.
Thank you, Professor.
Yeah, thank you. Thank you for listening. I will remove now.
Right, please. Thank you for a very an excellent talk. We enjoyed your talk, and a lot of statistics people here today. So I'm sure they'll appreciate your talk, and they can get back in touch with you. So we have
I will be happy to communicate with them.
Thank you very much. So move on to the next session. Next speaker, Professor Barry Arnold. Barry, are you there? Barry, are you there?
I cannot see him, but he joined yesterday actually. But,
right, I know. Barry, yesterday, of course, we talked. But I don't see Barry in the list here today.
Yes, I don't. I think I have already. Indonil has already sent him one email again with the same link.
Yes.
Yeah.
So should I think both Indranil and Shujit are here. So after Barry, Shujit is supposed to be speaking. If it's okay with you and Shujit, can we ask Shujit to prepone his talk so that Barry can give his talk later on if he's ready or if he's prepared to do so? Is that
Yes,
okay?
I'd be more than happy, Arishda, to give
Thank you for complying, Shujit. Yeah, I think maybe Barry is waking up, so let us give him some more time. Okay, and he'll understand you are taking his place. So no problem. He can.
Yeah, it's all up to you. If you want me to start,
I think it's better than it can be switched. He can have some more time. He'll be happy about it. I'll explain to Barry. Okay, I think with it's nice of Shujit to do us this favor, and I'll request Shujit to give his talk. Before that, of course, Shujit over here is from North Carolina State University. He is not a newcomer to this conference. He has been here before physically, and also I think also online before. So it's a pleasure to have you back, Shujit. Shujit is, as I said, is North Carolina University, NC State. He has worked in various areas, including multivariate analysis, biostatistics, and if you look at his talks, it's an array, different kinds of talks. So it's always a pleasure to listen to him. Sujit is a fellow of the American Statistical Association. He has many laurels, lots of good publications. And without any further ado, I'll request Sujit to present his talk. Over to you, Sujit.
Thank you so much, Aziza. I mean, for your kind introduction, and it's embarrassing to hear from you, but I really appreciate that. And can you all see my screen?
Yes, we can see your screen. It's visible, quite visible.
All right. So thank you, everybody, for the opportunity given to me to present some of the work that I've been doing with one of my students. And this came from some kind of an application we were trying to do in a lot of time in finance, in any type of weather events and so on. Whenever you were doing some kind of time series forecasting, the question is that nowadays we can collect as much data as we want possibly, but how much of those data are really useful, practically speaking? So that's the premise of this. So let's consider the stock prices because, well, this is the time possible. No one wants to look at this type of prices. I'm scared to look at my own portfolio, but nonetheless, these are adjusted closing prices of, I think, the company Meta, formerly known as Facebook. And if you look at this graph, I mean, of course, it's only up to 2021. So, but the question is that here, if I'm trying to, sorry, I'm going the other way. If I'm trying to make a prediction for the next 5 days or 10 days, which is good enough for stock prices data because I can change based on my prediction, my portfolio, and so on. The question is that will a very long time series data will lead to more accurate forecast? The predominant understanding of any statistical method is that the more data you have, the better you are off. But that is something that I'm kind of questioning itself, even under when the time series could be a stationary series. So let's see what's we get to see. So, or if I'm interested in the next 5 or so days of forecasting, is just looking at the last 1 year data is good enough, or should I look at last 5 years of data? So that's kind of the thing I'm trying to ask and go ahead. So basically, if you think about it, I mean, if I'm trying to forecast some values, no matter what model, but we have to discuss about what type of criteria I use to measure the accuracy of my forecast. So that's also something sometimes debatable. But nonetheless, do I need a binocular? That means do I have to look back all the way 5 years ago of the data? Will that be really helpful? Or I just need to look at what I do in while driving the car, rear view mirror. And you can see when we drive a car, we really don't need to know what's up there back 10 miles. I just need to know what up there for maybe 1 or 2 miles is good enough, right? And we make our decisions when we are driving the car and hopefully not making too much of those accidents. So that's what we are here today to talk about. So, and it is not just in terms of predicting stock prices. It could be applied to even weather events. For example, if I'm trying to forecast something for tomorrow, possibly I can do a very good job. Maybe a day after tomorrow, okay. Thursday, maybe. Saturday, who can say? And maybe Sunday, no idea, right? So, and typically in a lot of this application, I'm talking about this type of short-term forecasting. If I'm trying to do a long-term forecasting, the story might be different. But right now, in this particular talk, I'm talking about short-term prediction. So if I'm interested in predicting something in the next 5 or 10 days, or maybe up to 15 days, that's all. But then how much of the previous immediate past data would be useful? So this is something that my student Zinu Zhang at NC State and I have been exploring. And we actually have a paper submitted, and I'll refer to a paper that we have published already on the archive. So I'm going to talk about that there is actually kind of a dual efficiency aspect of it. That dual efficiency means that how much of data produces how much statistical efficiency, and there might be a compromise there. And I'm going to give you some numerical examples to the extent possible if the time permits, and some general conclusions. But this is something, an ongoing work. We are still exploring some of this. So time series forecasting is not a new problem. It is a coincidental problem in data science, and everybody is interested. In fact, although we do a lot of things in terms of parameter estimation, hypothesis testing, one of the predominant use of statistical methods is, I think, in forecasting, and the estimation is sometimes viewed as a filtering process. So in recent times, the data collection is very easy. I mean, we can do a very high resolution data. For example, stock price, we can do every minute, maybe every seconds. But how much of that data really are useful, practically speaking? I mean, just the fact that we can collect more data may not mean that we can make use of it. So the questions, the simple two questions I have is how much of time series data are practically useful, and what proportion of the long, because I'm questioning the first one and the answer is possibly not much, then what proportion of the long time series is needed to achieve a desired predictive accuracy? When I mean by desired predictive accuracy, it can come back to stock prices. Suppose I'm trying to predict something and I want to see if the prices would be few dollars or euros or whichever currency or rupee. If that efficiency, I mean, I'm off by maybe $2 or $3, practically that doesn't really matter much. So I'm willing to lose some accuracy in that sense, because practically that doesn't actually change my decisions. So if I'm willing to do that to some extent, how much of previous data is actually practically useful? Okay. So let's consider some notations. So suppose I have a time series of data, which could be any other correlated data. I'm not making particular assumption at this point, which I denote from 1 through n as x1, x2, xn. And suppose my goal is to predict the next h values. That h could be 5, 10, 15, whatever someone is interested, or 1 even. And that data set is what is I'm going to predict. And what is my goal? My goal is to figure out how many steps back from today, like from n backwards to n minus k plus 1. So going k step backwards, that performs forecasting almost as good as all the way from the first day collection of the data collected from 1 through n. So that's the problem. So clearly, in order to answer any of this question or achieve the goal of this research, we need to talk about what modeling assumptions are made about x1, x2. Modeling may not be just in terms of what it is an autoregressive process or not, but also in terms of stationarity, long-term stationarity, local stationarity, and so on. So what are the assumptions? And the second thing one needs to settle on, otherwise we cannot really answer this question, what criteria should be used to measure the accuracy of forecasting? Typically in statistics, we use squared error loss, and so mean squared error and so on, but that may not be always relevant or useful in practice. And so there are many other criteria, and the decision or the solution might change based on the criteria. So thus, we have a dual purpose in this case. We want to figure out the smallest proportion of the data, which are denoted by k over n. So k will take value from 1 to, so k is actually that kind of a tuning parameter, which is integer valued, which takes values 1 through n in a sense, or maybe n minus 1. And so we are trying to achieve that. And then the loss of efficiency is, if I use the MSE, mean squared error, as the measure of my efficiency, then it is the ratio of that. So typically this ratio is supposed to be bigger than 1, I mean, under certain modeling assumptions, because I'm using less amount of data by using only k data point, the last k data points, instead of the last all n data points. So this is supposed to be sometimes bigger than 1. But let's see what's in the framework. Sorry, I'm always going the other way. In order to understand this framework, I mean, what we are going to use is, or propose to use is sequential backsampling. So this is the entire data set, and this is the data that I'm going to keep for my validation. And then I am going to look at the last k values. And for each one of them, I'm going to calculate the forecast accuracy and see how much of the accuracy is lost. Sorry. It possibly helps to understand a little bit in theoretical, otherwise it gets too complicated. So let's consider the most simplest one and see even what we can achieve with this typical AR model. So let's consider weakly stationary mean zero autoregressive process. I mean, this is mean zero can be adjusted to any other mean, but for the simplicity, we are doing that. And then our goal is to predict the n plus t values, where t will be taking the values this. So the conditional expectation of the future values given what we have seen in the past, because it is so here we are assuming that we know that this is an ARP process and P is also known, but we are going to relax that in a few more slides. So in this case, the conditional expected value can be calculated, and these things are in any standard time series textbook, so there is not much explanation to be given. But now I'm introducing this k because what I'm going to do is that if I would have used only the last k values, then the estimate of the AR coefficients is going to depend on that k. So that's why this k is there. So phi hat of k is like that. And the forecast value of this based on using the last k values can be written down is like that. So basically there are two types of errors that can happen. One is the approximation error that we know. So, but this is something that we cannot use because that involves a parameter, but this is a theoretical error that is going to happen if I'm trying to forecast it. And then we have the estimation error, because I am going to estimate the parameters by some method, Walker or MLE or any other methods for AR process. So that's the estimation error. So in that case, the total forecasting error would be the sum of these two. And if I'm trying to estimate the or forecast the next age values, the MSE for by using k data points. So now the k here denotes that I have used only k many values from n minus 1 all the way to n minus k plus 1. So that if I decide to use MSE, then this is the thing. So one might challenge that why I'm using that, but this is the predominant use in statistics, so we are using that. And then the relative loss of forecast accuracy will be given by this, right? But as I said, there is no need to use mean squared error. We could use, there are a lot of other forecast accuracy error that are used these days. For example, this is the mean absolute error, which is given by that, or this is on a relative scale. So there are, and RMS is basically square root of that. So these are all of this type of errors that make sense depending on what is the particular application. But the framework that we are working on, it really doesn't matter what that is. The only thing is that this ratio would be replaced by one of these measures that one is interested in. But again, for simplicity and for some theoretical purpose, I'm going to still keep using MSE, but in our paper, we actually show applications using some other measure, which is not going to be part of today's talk. So what is the dual efficiency framework? So to understand this from a theoretical perspective, basically, I want to achieve something like this. So I want this thing. I know that possibly by discarding the long past value, only using the k values, possibly I'm going to lose some efficiency in terms of that efficiency ratio measure that I mentioned using MSE. So I understand that this thing would be likely to be bigger than 1, but in limit, and this is a random quantity, so we have to find the probability that it is less than 1, so plus that, and this is the efficiency loss that I'm willing to lose. And as I said, in applications, if you're talking about this epsilon in dollar amounts, we are talking about say $1 or $2. It doesn't matter if I'm trying to predict stock prices, and I'll be off by a few dollars or so on. So that is practical. So this is the practical efficiency part. But at the same time, this is the another one that I don't want to keep using a lot of historical data. Ironically, the thing is that the modeling assumptions are more violated if I use a long time series data, because stationarity of a long time series is questionable than stationarity of a short time series, because you can think because of change of support, or there will be a threshold models. So all those things actually are more likely to be violated if I assume the whole 5 years of data remains stationary, which is actually more unrealistic than assuming only. So that's the reason I think these things are going to work. But in theory, because this efficiency measure itself is a random quantity, because we are actually estimating parameters and so on, we are going to derive some kind of asymptotic equivalent, which I'm going to call A. A stands for the asymptotic equivalent version of that one, so that these two conditions would be satisfied. So the question is that how much fast we can let this epsilon n goes to 0. That means how much close to that full efficiency we can achieve in terms of asymptotic theory. So the result for that that we have so far, I mean, this is particularly only for AR models. I must say that this is not being generalized to the any other model yet. This type of theoretical derivations are not new and has been done. And here I'm just putting that formula, but more details are in the appendix of the paper that I'm going to say where it is. Right now it's under review, but also it's on the archive. So the first result is that the asymptotic value of this predictive ratio in the case of ARP is given by something like this. And using this, it depends on the parameter values, A and B, which are these things. Interestingly, this ratio actually is not going to depend on sigma square, which is the error variance. It is only going to depend on the AR coefficients. And these things are actually estimable, because these things have this closed form formula. So if I have estimates of these things, I can just plug that in to get an idea about this. So now, even for this weakly stationary ARP process, this first somehow might sound counterintuitive, but it looks like we can achieve the full efficiency at a very accurate rate, because if I let that epsilon go to 0 at 1 over n, right, so it is pretty fast if n, because time series if n is very large. And so this is theoretical. We don't know the lambda value. So this is the kind of amount that we are willing to lose in terms of efficiency. One can show that this optimal k that I'm trying to find has this asymptotic expression. And you can see from this k over n, clearly, I mean, this thing is less than 1, and this thing we are determining anyway. So that gives you an answer to that. So at least for this type of process, for a general AR process with P values, I mean, here we can have this result, and that tells you that in theory, this does exist, and we can achieve a high level accuracy. But let's see with some numerical illustration. So suppose I take this model, and this is, I think, is simulated from actually an AR5 model, and I look at the predictive ratio. So you can see that here the blue one is about predicting the next 3 days, the orange one is about predicting the next 5 days, and the gray one is predicting the next 10 days. So for all of these future values that we are trying to predict using data, I mean, here n is 100, 250, 500. So, I mean, it takes a certain amount of data to achieve this one. So this one here represents when I'm using the full data, all 100 values. Here I'm using all 250 values. Here I'm using all 500 and all 1000. But the k, this ratio is k over n. So when the ratio of k over n is 0.2, so that means I'm only using 20% of 500 data points. It almost achieves that issue. And I mean, in theory, I mean, we know that this is going to happen, and it depends on the parameters that being used to generate the data. But nonetheless, it shows at least numerically, and even for 1,000. So it looks like there is not much point in keeping all 1,000 values, previous values, if I'm still going to achieve certain, and it doesn't matter what horizon I'm looking at. They have the same phenomenon, and because it's a random quantity, it even shows that we can actually get better estimates. But this is a random quantity, so this might happen because of random fluctuations and so on. But nonetheless, asymptotically, we know that this is there exists such a k, and in this case, that k opt is something like achieving within 20%. So looking at this, I mean, for stock prices, typically there are 250 days in trading days in a year. So, and that basically says that a year worth of data is good enough if I'm trying to predict the next 3, 5, or 10 days of forecasting. So here we have assumed that we know that is an AR process. So this is exactly what I said. I mean, with only 30 to 60%, it can sometimes even get better accuracy than assuming using the entire data points. But now the question is, what happens when the true model actually ARP is not known, or the values are estimated, or what happens the model itself is misspecified? The things becomes more interesting. But then we need some kind of a model selection aspect built into the framework, because in earlier illustrations I used that I know it is an ARP model, but now I'm relaxing that. So it could be any data generation process, but then we need to build a framework to. So again, the idea is similar, but each of these k data values, I have to split this into train and test, so that I use some of the machine learning methods like convolutional network or all these neural network models. All this can be used because they are sitting. But in this case, because it's a time series data, we don't have to have a random split of the data. We can just use the last PM values, and then we can test it. And that way we can build the model. And we have to satisfy certain basic minimum requirements so that the models can be built. So this is one addition to the previous framework that we need to do, because now we are relaxing the fact that I don't know what the model is. But without going into theoretical results, so I'm going to show you some of the plots in the interest of time. So in this case, I mean, we are going to compare the oracle. Oracle meaning that here I know what that model is. In this case, still say AR5, but I don't know it is 5. I'm going to estimate the order of the AR model itself. And there are many ways of doing that. I'm actually using some kind of a lasso method to do that. I kind of estimate that order P. One can use AIC, BIC, but I'm using lasso, adaptive lasso, or adaptive elastic net. So these have become much more popular than the information-based criteria because we are not using the likelihood-based approach all the time. But amazingly, even when I'm trying to estimate the order of the model, the same phenomenon that I have seen with the Oracle model shows up. So again, it shows that even if I would have estimated that, and if I'm using adaptive lasso or elastic net or any versions of those machine learning methods, we see the same phenomenon. But now, suppose even I say that, well, it is not even an AR process, it is some kind of a threshold autoregressive process. And this might be true in a lot of cases. So that means the model is generated from a model like this. This is again for illustration. But as an user, suppose I don't know that. So I don't know that this is coming from that. But erroneously, I still fit an AR process. So it's a threshold autoregressive process, but when I'm trying to model, I don't know that, I'm going to still use, say, erroneously an AR process. And then again, use adaptive lasso, adaptive elastic, and auto-tuned elastic net. Again, I don't have time to get into all of this, but this is not our contribution. This are there, and there are excellent R packages to implement some of this. But now let's see what happens to this dual efficiency framework. Things become interesting in this case. So here it says that, well, I mean, when n is 100, 250, this, And then here the horizon is 1 day, 3 day, and 5 days. I mean, it says that even with the model misspecified, the similar phenomenon happens, but it tells you that by assuming a wrong model, you really are even worse off if you have used a very long time series. It is similar to what the MLE phenomena sometimes. So if I am using the right model, MLE is best. But if I'm using the wrong model, MLE is the worst, because it is going to go towards the wrong very fast compared to some other robust methods. So that's what the phenomenon is saying that, but it says that eventually, I mean, it hits this efficiency ratio of 1. I mean, in this case, 1 means that I'm using the entire data. But so initially we are going to lose, but then it comes back to that. So again, it is pointing out to the fact that we really don't need all the past values to be used for accuracy, achieving accuracy by using all data points. So let's, so those are, and there are a few more examples in the paper, but let's come back to the stock price data that I first started with my motivating example. And what is done instead of stock price itself, you look at what is called a log return, so changing the values, because we really don't care much about what the exact value is. All we want to know how much it would have changed from previous day or day before yesterday and so on. So that's why we are looking at this log return values. And we are going to illustrate these things over other non-stationary machine learning methods. So in this case, again, I'm trying to predict the 3 days ahead, 5 days, and 10 days, and these are good enough for stock markets. And this is looking at Amazon prices, Google, Facebook, and Apple data. And we see a similar type of phenomenon, like depending on particular stock prices, they might have been generated from any type of model. We have no idea. No one knows what these true models are in this case. But we see similar phenomenon that sometimes we can achieve much actually better accuracy than using the entire data points. And,
Sujit, you have 2 more minutes.
Yeah, I'll be fine with that. Exactly. Thank you. So, and now it shows the applications of various. So if I use an autoregressive model, autoregressive with lasso and elastic net, ARIMA, GARCH, AGARCH. So there are lots of models that are available. Interestingly, for all of this, we see very, very similar phenomenon in the sense that we possibly don't need to give more than 20 to 30% or so, which is roughly coming to a year of data, at least for this type of stock market prices. And here I'm looking at RMSE as the measure of accuracy. And we have looked at changing that to some other criteria. And also we have done an application with the COVID data and so on. And we amazingly see the same. So for this, we have not established any particular theory because the theory was based on still AR process because things can be derived. But this is something that needs to be worked on. So to give you some kind of numerical one, so here, suppose I use the entire data sets, then and I look at various models that are typically used for stock prices or the log return values prediction. Here the RMSE that is the best achieved by this GGR GARCH model, I don't have time here, would be this value. But it says that if I would have used just an ARIMA model with only 208 instead of, so here, instead of 1000 values here, again, is that we would have achieved a better RMSE than this one. And some of these RMSEs are actually better than any of the RMSEs that uses the entire data. So you can see that these things are all less than that. And this also tells you that dual efficiency, how much it is achieved and so on. So this clearly points out that in terms of when it comes to prediction, the usual folklore that more data, the better the accuracy possibly is questionable. So with that, I'll like to make a few points that I already made. I mean, so I think these things I've already mentioned. So in terms of this talk, I mean, the conclusion is that long historical time series may not always lead to more accurate forecasting. And what we proposed is a kind of a more of a framework. It is not what model you used, what accuracy, but this is possibly one way to look at whenever you are looking at forecasting. So this dual efficiency these days, I think sometimes it is overused, that more data is better. That is questionable. And even under some AR process, we have established theoretically that this is actually feasible, but more work is needed. And with that note, I think I'm going to stop here and take questions if you have any. And if you're interested in more details on the theory and more applications that we have illustrated, the paper is available on the archive. You can just Google this or just type in dual efficient forecasting. And I think since I have presented actually in another company's conference, if you Google, you will find it very quickly. So thank you very much for your attention, and I'm ready to take any questions.
A quick question, one question. We have time just for one question. Okay, Shujit, it looks like there's no question, but your results, your conclusions are quite sensible. I think it is expected, and especially with high volatility. With nowadays, the market showing the high volatility, nobody would use a very long-term series. I think that is well understood. So your results go to prove that with theory and with support from the data. Very interesting talk. Thank you, Shujit. Okay, thank you very much. Okay.
Thank you.
Okay. So let's move on to our next speaker. Barry, you are here? Here.
Yes, sir.
Good. Thank you. Welcome to the party, Barry. So we thought we'll give you a little bit more time to come to the talk. We waited for about 5 minutes, and then Shujit was really helpful to us. He said, okay, he'll take over. We did not.
Yeah, I appreciate them.
Yeah, we do too. And your slot has now been just shifted. You are there. We very much want you to speak. So without any further ado, Professor Barry Arnold is known to the entire statisticians group. In India, he's very, very well known, of course. His presence has been lively and definitely an inspiring one. And today, it's a very great pleasure for us to have Barry in our conference. Barry has lots of laurels, more than, I think, almost 300 papers, huge number of books, lots of PhD students. He has traveled wide and far in many countries, giving lectures, having students there. And in India, of course, has been one place. Definitely, Barry has come back. We enjoyed his presence here. And he's a fellow of the American Statistical Association. He's a fellow of IMS and many other laurels. So we can go on and on and on. But definitely, it's a big pleasure for us to have Barry speak in this conference. Barry, over to you, please. You have 30 minutes.
Okay. Okay.
We need you to share your slides.
Can you see it, guys?
It's coming up. It's coming up. Give a sec. Yeah, it's there, Barry. Great. Fantastic.
Okay. First of all, I apologize for messing up the schedule. My alarm was really set for 4 a.m., but it didn't go off. It went off at 5:30, which is my usual time. And so I rushed over here, threw on a shirt, and here I am. Thank you very much for inviting me to talk to you. It's a great pleasure to be in Kolkata, at least theoretically. And for those of you who are not, who haven't been to Calcutta very often, I thought I'd show you a picture of the very idyllic scene close to the place where the conference is actually meeting. But if you had come to Calcutta, you would have to have gotten to this idyllic scene by road. And this is a nice picture of Calcutta traffic. And I guess it looks like it might be raining. There's a guy with an umbrella, but it works. So even if you had to come that way, you would have gotten here. Okay, again, it's a pleasure. And again, my apologies for keeping you waiting.
Your slide is not moving, Barry. Your slide is not moving. No, it's moving, not moving. You have to go on to the next
Huh.
slide.
Is that?
No.
Did it move back to us?
You click on the next slide maybe, or click on the arrow. You are on the first slide.
Yeah. I know. Okay, did it change?
No, not yet.
I think if you click from beginning or something, that on your slide, it will work.
Okay, it didn't work, huh? It's up.
Can you click on the right and the left panel? The slides are showing. Click on the second one on the left panel. On the
Okay, let
left
me get my
panel that you have the slides there, showing all the slides on the left. You click on the second one.
Yeah,
the second
from
one.
the current
Click on the
slide.
second- Click on the second one.
Mine's changing. Is yours not?
No, it's not coming up yet.
I think it is possibly not in the presentation mode, that one we are looking at. So there is a little button in the presentation mode.
No, but his first screen is there. We can see his first screen. Can you click on the second one to your left? Yeah, just click on the second one to your left. On the in this panel, on the panel to your left, where all the slides are there listed. Click on the second one after your title slide. The second one at the left panel.
Okay, here's the first one. There's the second one. There's
Click
the
on the
third
second
one.
one. Can you click on the second one with the picture that you are about to show us?
Yeah.
That is on the left side on the panel. Can you move it to your left? Click on the second slide.
Oh, I had the slideshow going.
Yeah, you are moving slowly. Yeah, why don't you are almost there? Your mouse is not in the second slide.
I don't know what's going on, Ashish. I don't know how to do it any other way. I can. This is the there's
Professor Arnold. Are you using?
Yeah, here you go.
Yes, it's
Got
moving.
it.
Yeah.
Got it. It's moving. So you do that. I think that's the easiest way right now for you. You move. Just click on the second slide and third slide. That way it will come up. Okay, we can see it.
Okay.
Yeah.
Can you see
Here's your
that now?
graphic jam. Here's your favorite
Okay.
calculus graphic jam. You can see it.
Okay. Yes. Okay. You can see, even though I don't have a full screen, it's okay. You can see it, right?
Yeah, I can see it. Good.
Okay.
Click on the
So
third one.
let's see.
Yeah.
Okay. Here we go.
Yeah.
All right.
Okay.
Yeah.
Good. It's working now. Great.
Okay.
Good.
Okay, why characterizations? Okay, sorry for that delay. They help us understand the consequences of common distributional assumptions, and they're sometimes useful for testing distributional assumptions. My example that I usually give is if you assume normality for heights of kids who have specific weight and normality for weights of kids who have specific heights, that's not enough to characterize the classical bivariate normal model. A much more general model exists. So you have to understand the consequences of your assumptions, and usually that's done by asking yourself, what is the class of all distributions that satisfy the assumptions that I'm making? And it's often bigger than what you want. Okay, let's look at today's topic. We're going to talk about several things. Characterizations that are motivated by the fact that there's a link between convolution and size biasing for exponential random variables. I'll explain that link in a moment. I'm going to talk about some things called size bias convolution pairs. And I'm finally going to put in discussion of records and linear combinations of observations, both in discrete and continuous cases. There too, it's going to be exponential characterizations. Most of this work results from work with Jose Villaseñor from Colegio de Postgraduados in Mexico. And so any mistakes are his. No, that's not true. He's a very helpful and creative partner for me. As we move along, we're going to encounter many characterizations, and we're also going to meet up with a lot of conjectured characterizations. And I'm asking you if you have any interest to suggest or may pass on your ideas that might help resolve these suggestions. To that end, if you are interested at all, don't try to write them down as we go along. I'll be happy to send you copies of these slides if you just send me an email, barry.arnold@ucr.edu. Okay. Let's look about how things work for convolution and size biasing. First of all, some notation. Xi's for the random variables, Sn for the sum of the first n of them. They're assumed to be IID. We're going to use Laplace transforms, which are defined to be expected value e to the minus sx. And that's the right tool for positive random variables because you don't have to worry about existence. You don't have to worry about that little niggling problem of making sure your moment generating function is defined in a non-trivial interval that includes the origin. And you don't have to worry about complex variables if you, which might occur. You might have to do complex integration if you play around with characteristic functions. So if you're talking about non-negative random variables, Laplace transforms is your tool. The convolution notation we just have here, this is the distribution of the sum of two independent random variables, x and y. And it's just think about it as being conditioning on the value of y. For x plus y to be equal to x, y must be equal to something less than x, and then x must be equal to x minus y, and sum over all y. So that's pretty obvious how that's working. Okay, now we know the following fact. This is the crucial thing that we're going to build on. If we have two independent exponential random variables, then the distribution of their sum, or the density of their sum, is just a size bias version of the density of one of them. It's also could be known as a weighted distribution with weight function x. Okay, I claim that it's this property only holds if the x's are exponential. I'm just going to sketch out the proof. We'll go real fast. First of all, the Laplace transform of the sum, since their IID is the square of the Laplace transform of one of them. And then the Laplace transform, then the right-hand side expression, which was here, if you look at its Laplace transform, this is the formula. And that can be written as the negative of c times the derivative of the Laplace transform. Well, that's a simple differential equation. Even I can solve it. And the solution is of this form. And since it's a Laplace transform, its value at 0 is 1. So that tells you that k is equal to 1. And therefore, we have our exponential distribution. Okay, so that's pretty good. After seeing that result, you can think of a whole bunch of parallel results which might be true. Some are true, some are proven, some are challenging, and others are just conjectures. First one, first variation, think about Sn to be the sum of n of the x's, and let's look at the density of the sum of k plus one of them. And if that's a weighted distribution, a weighted version of the density of the sum of k of them for some fixed k, then I claim it's also an exponential distribution. This time the mean is equal to 1 over ck. And surprisingly, in that case, once again, using Laplace transforms, first using the definition, we get this equation, but you can cancel out L to the k plus 1, L to the k minus 1 from both sides. And lo and behold, you have the same equation you had in the previous theorem with c replaced by ck. So we have an exponential distribution. Then another one, if you have a convolution of two densities f and g, which is equal to a weighted version or size bias version of f, okay, where if you know g is an exponential density, then you can prove that f must be a gamma density. Okay, and it doesn't work for any other density. Gamma with any shape parameter, and it will have the appropriate scale parameter that is determined by the density f that's in this equation. Once more, you use Laplace transforms. Now, having done that, it's very hard to resist the temptation to consider, instead of x, have a weight function which is x to a power. And to start with, let's just consider x squared. If that's the case, if we have the sum of two random variables, and for some positive c, we have that the density of the sum is a weighted function of the density of one of them with a weight function x squared, well, I have to put in a regularity condition here, which I'd love to get rid of, but I don't think I can. I think that if you don't have this satisfied, then you'll get other solutions. And notice this condition is a property of the gamma distribution with shape parameter 2. If that holds and the convolution formula gives you a weighted density with weight function x squared, then it must be a gamma distribution with shape parameter 2. It's a little bit harder to prove that, but eventually Laplace transforms save the day. Okay. Well, a conjecture that follows from that, it's inevitable that you would hope that you could do better. What if you said, instead of x squared, x to the alpha? Well, what we've seen is that when alpha is equal to 1 or 2, we know that this equation characterizes the gamma with the exponential, which is gamma with shape parameter 1, or the gamma distribution with shape parameter 2. We think in general it should characterize a gamma density with shape parameter alpha. This is harder still. This is one that Jose and I have battled with, and it's still open. So if you can do that during the rest of the talk, or maybe tonight when you're riding home on your bicycle, then let me know. I'll be pleased. More conjectures. This is the more general one that we could come up. Suppose we just look at a fixed pair, n1 less than n2, and assume that the density of the sum of n2 of the random variables is equal to a weight function, a weighted version with a weight function which is x to the n2 minus n1 of the density of the sum of n1. We know this is true for n is equal to 1 and n1 equals 1 and n2 is equal to 2, but we think in general that's going to work. And that tells us it's an exponential distribution. That one we have not been able to resolve. Now, one of the things that happens when you're studying exponential distributions is that you can always think of a parallel statements that involve geometric distributions. And in fact, there's usually a sort of a parallel situation where the gamma distributions are sort of replaced by negative binomial distributions, the exponentials by geometric distributions. And in fact, sometimes you can prove theorems about the exponential distribution by taking limits using the fact that a constant times geometric, if you choose a Cn times x, where x is geometric, that converges in distribution to an exponential, so that you can sometimes get a free lunch there. Okay, so it turns out here better results are available in the discrete case. And so this is the exponential. We have a geometric random variable instead of exponential. Here's our geometric characterization that's parallel to our first one. Two IID non-negative integer valued random variables. We're going to suppose that for each k and some c, this is the density of x1 plus x2, and it's a size bias version of the density of x1. It's got k plus 1 instead of what you might think of or might expect to see k here. It doesn't work with k, it works with k plus 1. And effectively what this is the density of S2 divided by the density of x1, discrete density in both cases, is just c times k plus 1. If that happens, then it must be a geometric distribution. The tool here is to use probability generating functions, which are really just Laplace transforms, but they simply in the integer value case, we can do things a little better and a little more simply by using PGFs. What we do is we get from this expression, we get a differential equation for the generating function, which is easily solved just as we could do in the continuous case. It's a more general result. If you have a bunch of IID random variables, then if you look at the density function of the sum of n of them, divide that by the density function of the sum of n minus 1 of them. If they were geometric, notice my geometric distributions have possible values 0, 1, 2 up to infinity. Okay. So they're the number of failures that precede the first success. That ratio is just p times 1 plus k over n minus 1. Well, I claim that if that happens, then it must be a geometric distribution. So that parallels the case that we saw before. Once more using PGFs, and once again, the same differential equation has to be solved as was the case n equals 2, just like was in the case for the exponential. In fact, we can prove an even more general result, which was parallel to the conjectured result that we couldn't do before. We're dealing with the case of n1 less than n2, and we're looking at a sum of n1 of these integer-valued random variables, Sn1. Its density function, okay, we sum of the density function of discrete density function of the sum of n2, divide that by the discrete density function of the sum of n1, and you get this quantity here if they're geometric, and only if it's geometric. So we can characterize a geometric distribution by effectively the ratio of the densities of Sn1 and S sub n2. Okay. Well, just to illustrate how that's going to work, I'm going to look at a Poisson characterization, which is sort of a little bit out in left field. And I'm going to assume now, if you have IID Poisson random variables, then Sn will have a Poisson n lambda distribution, right? Because the Poissons have this additive property. And so for the case of Poisson variables, the density, if you take the discrete density of n2 of them, which is Poisson n2 lambda, and divide that by the discrete density of the Poisson n1 lambda, you get this expression here, n2 over n1 to the kth power. That observation, that only happens for the Poisson distribution. So here's our theorem. If the ratio of the two densities of Sn1 and Sn2 is of this particular form, then we have a Poisson distribution. I'm going to suggest how to do that. It's tempting to try to resolve the issue using probability generating functions because that works so well in our other characterization problems. But if you do, the generating function must satisfy this kind of equation. The nth power of p is equal to c times the n first power, evaluated not at s, but evaluated n2 over n1s. Now, I don't know how to solve that equation. Now, here's one where you might be able to help me, okay? I don't even know, I don't think, how to solve it when n1 is 1 and n2 is 2, but that may be easier. Okay. Now, instead, we can make progress by just looking at the condition that we had for a series of values of k, starting with k equals 0 and moving on, etc. If we denote the probability that x1 is equal to I by p sub I, okay, which is reasonable notation, and also denote the ratio between P0 and P1 by lambda. That's not a restriction, okay, because P0 and P1 could have any relationship whatsoever, and this lambda could be any, the lambda must be positive, but it could be any positive number. If you look at the case k equals 2 of our magic equation here, okay, oops, this equation, k equal to 2, then you get from that P2 is P1 squared over 2P0, which is lambda squared P0 over 2. That's encouraging, right? We're trying to prove we have a Poisson distribution. Try k equals 3, we get P3 is lambda cubed over P0, 3 factorial. Like eating potato chips, you can't stop. Use induction, and you end up with Pn is equal to lambda to the n times P0 times divided by n factorial. Okay, and by induction, we can conclude that x has a Poisson distribution. Okay. Now, it's quite plausible that the ratio of the densities of Sn1 and Sn2 would determine the distribution of the x's. Okay. In the absolute continuous case, this conjecture is open. In the general case, we can make some progress. In fact, we can actually prove this result with a one condition that's extra. Okay, so here's our situation that we have. Let's let xi stars, so we'll fix a particular density for the x's indicated by an asterisk, okay? And they'll have density probabilities pk star, and we'll let Sn star be the sum of the first n. And then we're going to define for any n1 less than n2 the ratio of the densities of n1 and n2 and n1, and denote that by A star n1 n2k. So what we're doing here is we're talking about the ratio of the density of Sn2 to Sn1 for this particular distribution. We claim that if we have another sequence of x's which has the same ratio as densities of sums as the xi stars, okay, we know its ratio of densities is also equal to this, and if the one extra condition we have to put in, if they each have the same probability that x1 is equal to 1, then they must be the same density. So essentially, we have proved that the ratio of the density of Sn2 to that of Sn1 characterizes the distribution. And again, it's an inductive proof, but it can be done. And a corollary is that you can deal with random variables which have a bounded support, because in that case, you only have to go up. If they're all less than or equal to m, you don't have to complete the induction. You just have to go n steps of the induction. Okay, convolution size bias, once again, if f and g, if f has an exponential distribution and g has an exponential distribution, then the pair fg, it has the property that that g that the convolution of f and g is a size bias version of f. Okay, and so we'll say if f and g are legitimate densities that satisfy the size bias condition, then the Laplace transforms must satisfy this equation, which is the same thing we've seen before. But equivalently, we can write this down this way. It turns out that that is a characterization of the fact that f is infinitely divisible. So the only time you're going to have these convolution size bias pairs is if f is infinitely divisible and g is the appropriate density that shows up here. So the characterization is fg will be a size bias convolution pair if f is infinitely divisible and the corresponding g has a Laplace transform that's determined by this equation here, or this one, whichever one you wish. And for example, if you choose a gamma distribution, then you can effectively conclude that the density of f must be exponential. And that characterization actually, example, if we wish to identify all possible densities where fg constitutes a size bias convolution pair, with f being a gamma distribution, it follows that g must be exponential. That's actually something that's appeared in the literature. Khatri and Parkes and Khatri, Sen and Khatri have all talked about this in the late 20th century. If we instead take an inverse Gaussian distribution, then it turns out that the corresponding g function corresponds to a chi-square distribution. And finally, if you have a generalized inverse Gaussian distribution, surprisingly, you can work that thing through with a little skill and decide that g must be a linear combination of gamma densities with actually a convex combination of gamma densities to be a valid density. Okay. How am I doing on time, Ashish?
You can have 3 more minutes.
2 more minutes. Well, I'll do my best.
Not two. 5 more minutes.
5 more minutes. Okay, well, I can finish in 5 more minutes. No trouble.
Right.
In a sequence of IID exponential random variables, the sum of the first 2 record values is a simple linear combination of exponential variables. That happens because for exponential variables, the inter-record times are IID exponential. So here's the property that for exponential random variables, x1, x super I in parentheses is the ith record. x1 plus x2 has the same distribution as x1 plus 2x2. Okay, so we say that the sum of the 2 records has the same distribution as a linear combination of 2 independent observations. Conjectures that we can come up for that are, suppose that if that's true, then we conjecture that f must be exponential. Conjecture 4, suppose that for some n, the sum of n, the first n records is equal to a linear combination of the first n observations. Then again, we think it should be exponential. And finally, to make things easier, perhaps, or harder, suppose this works for every n, then it should be exponential. Let me tell you about our work with those. We can prove the first one if we assume monotone failure rate, which is a very strong assumption. I'd love for you to relax that. Even then, it's a bit tricky, and I'd like to know if you can dispense with it. Conjecture 4, which was to see if for some particular n not equal to 2, you have this kind of relationship. That thing is unresolved. Conjecture 5, it turns out, can be resolved if you assume that the xi's have a finite 1 plus deltath moment, because in that case, all moments of the record values exist, and a little bit of algebra says that the nth record is n times the expected value of x1, which means that you know the sequence of expected values of all the records. And due to an old paper by Kermani and Begg, that's enough to characterize the distribution. And in fact, if it's n times the x, it has to be exponential. Whether that moment condition can be relaxed is another thing you can resolve while riding home on your bicycle. Okay. It seemed to be going backwards or forwards. Okay. 7. Okay. The assumption conjecture 6. What's conjecture 7? Is conjecture 6? Proof of conjecture 6. Okay. Okay. I think that somehow I went past record values. Can you dispense with this conjecture? 4 is 5 we resolved. That's conjecture 7. Oh, okay. Suppose that for some positive integer,
next slide is conjecture 6. Barry, your next slide is conjecture 6. Proof of conjecture 6.
Okay. Okay, here we are. Conjecture 6 says that if the sum of the first two records is the linear combination, then it must be geometric. Okay, that's the one that we can prove with the regularity. Conjecture 7. Okay, we haven't got that one. And conjecture 8, 7 is open. 7 is open. Thinking about conjecture 7, with m greater than 2, we don't know what the answer is. We think that other solutions are possible for m equals 3, and as a consequence, we think for n greater than 3, we therefore think that the hypothesis is highly doubtful. So basically, we don't think conjecture 7 has much chance, but we could be wrong. And again, any help will be appreciated. At which point, I think I've used up most of the 5 minutes that Ashish kindly gave me, and I probably have abused your patience. Thank you very much for your attention. Here's a picture of my home campus, and here's a picture of my hometown beach. It's usually filled with surfers, but this picture was taken during COVID. So we too suffered with COVID. Thank you again for your attention, and again for your patience.
Thank you very much, Barry, for your wonderful lecture. Lots and lots of problems for the youngsters, for us also, of all ages, and it could enough to keep them busy for a long, long time. Okay.
Okay.
Thanks again for your wonderful talk. Any question from the audience? Anyone? You can raise your hand, please. No. Okay, then for the sake of time, I think we should move over fast then. Okay. We'll move on to the next speaker. Indranil Ghosh. Indranil, welcome. It's
Thank
good
you.
to see you. Indranil also has been one of our speakers in the rather say star speakers in this conference. He was here last time, right? Last year you were here.
Yes, Professor.
Yeah, you might have been there also. So I had known Indolin personally, but that's another story. In any case, Indolin is from the University of North Carolina, and he has been PhD, so University of California, Riverside, and you can see his mentor working on the same area, distribution theory, which I'm sure has a lot of influence on Indonil. So Indolin continues to work on distribution theory, lots and lots of distribution theory, then hidden truncation models, then both Bayesian and non-Bayesian aspects, and on the size bias sampling also. So we see in his talk today going to hear about some properties of stop loss moments under biased sampling. Indonil, it's a pleasure to have you here. Go ahead with your talk. You will have 30 minutes, but if you can wind up a little early, we'll appreciate it. Okay.
Thank you, Professor Sengupta, and I'll make sure that I will wrap up in well within the time. Please let me know within 7 to 8 minutes before, so that I know where to stop. And it's a pleasure. And I thank Dr. Abhishek Odhikari for giving me an opportunity to present some of the works that I'm working on. So let me quickly share my screen. And okay, and is it visible now, Professor Sen?
Yeah, it's visible.
Okay,
fine.
Thank you. So today I'm going to talk about some properties of stop loss moments under bias sampling. And this is a joint work with Professor S.M. Sunod from the Department of Statistics and one of his student, Dr. Vipin, currently is at the Department of Data Science, PhD. And I must say that with all due respect, that I was invited to join in this project. So I'm not an expert on this field and I'm still learning. So my contribution to this work was on trying to see what are the relations possibly with the hidden truncation, and if so, how we can come up with some efficient estimation. But for the sake of time, I'm going to consider some of the interesting facts of these properties of stop loss moments under bias sampling. So here is the outline of my talk. Why stop loss moments, some useful definitions, possible areas of application. Mostly so far we have been able to identify in financial arena. Then we talked about stop loss moments, which is of course dependent on the stop loss distribution. Then I'll briefly talk about one particular example, like one particular family of the Pareto distribution, Pareto type 2, how to construct. It's a very simple one. And then there are some dependence measures that I'm going to talk about. I'll wrap up my talk. By the way, this work has been published in Journal of Applied Statistics in April. And again, my contribution is only on the hidden truncation aspect and some properties. But if you have any questions, I'll be more than happy to share with my co-authors, and we will respond to your email or questions or doubts. So in summary, well, stop loss moments have generally used as a useful summary for analyzing data that exceeds specific threshold levels. And I'm going to come up with an example very quickly. In many scientific studies, I mean, it is well known, at least to the statistics fraternity, that there are very different situations when sampling units cannot be recorded or collected with equal probability. And in such a scenario, selected sample units appear with unequal probability, and for example, with different weights, and that leads us to a biased or weighted sampling. So that's the connection we have with the stop loss moments in bias sampling. So here is some useful definition to start with. So if X be a non-negative continuous random variable with a PDF F and cumulative distribution function capital F, then the rth order univariate stop loss moment about the point t is given by equation point 1. Well, it's integral t to infinity x minus t to the power r fx dx. And the way we define is x minus t lower suffix plus. It's defined in that equation that represents the amount by which x exceeds a threshold t. Now, of course, there is a lot of interconnection with the weighted distribution in the construction of stop loss weighted distribution, even in the univariate case, as well as for the bivariate scenario. So the more general weighted functions, such as given by Wx, which is of this form, x to the power c1 and other three quantities floating around. So for example, if C1, C3, C4 you set equals to 0 and C2 equals to 1, this would be the moment generating function. If C2 0, C4 1, then it's the probability weighted moment. So this is the more general form that we utilized in the paper for some specific choices of C1, C2, C3, and C4. But you could have all of these different quantities like order statistics, proportional hazards, and proportional reverse hazards. Now, in the construction of univariate stop loss weighted distribution, we considered the weight function to be of the form pi of t, just setting r equals to 1 in equation point 1. And that this particular random variable, x minus t lower suffix plus, is utilized in defining partial moments that are meaningful in the study of personal income. So if X represents the income of an individual and T is the tax exemption level, then this random variable, X minus T lower suffix plus, that represents the taxable income. So income which falls short of tax exemption level T is of no effect in the computation of how much tax you owe or you would be refunded, and therefore is treated as zero. Now, therefore, the study of partial moments is useful in analyzing measurements that exceeds the threshold level without the truncating the distribution at t. And there have been so many research works that are well exist in the literature, and this quantity is interpreted as the residual life in life length studies, such as we found in lean. In actuarial science, this particular random variable represents the financial loss incurred by an insurance company known as risk. And this general pi RT, that represents the rth degree stop loss transform of the risk X and is a standard measure of dangerousness of X. So, I mean, in our first review of this paper, the reviewer asked for some real life application, and this is what I was able to figure it out in the context of application of these stop loss moments. And Nair, with his co-authors in 2018, have carried out an extensive study on bivariate stop loss transform in the context of reliability analysis. However, my two other co-authors for this paper, Sunoj and Vipin, they have extensively worked on the stop loss transform and various other associated properties. Now we move on to the weighted version. So if X upper suffix W denotes a non-negative univariate weighted random variable with an absolute continuous survival function of this form, then the weighted stop loss transform can be defined, and you could only see that the only change from equation point 1 is that it is the weighted version of the density function that are used here. Now, there are several properties that you are able to establish in the paper, such as this weighted version of stop loss moment uniquely determines the corresponding weighted distribution if you take the derivative of order R, and that the right hand side should look like this in equation point 3. And of course, when t equals to r equals to 0, it is the survival function for the weighted version. If t equals to 0, then the first order, r equals to 1, then it is the expected value of uh, the weighted random variable. And this stop loss weighted moment is a convex function of t. It is non-decreasing in function in r. And Moreover, several important reliability concepts such as the failure rate, mean residual life function, etc., and their properties can be reinstated in terms of the partial moments. And there is a very nice paper by Sankaran and Nair, and which they have discussed in different contexts, but there we find that such relationships are really, really useful, and it gives us an important and unique tool in analyzing the statistical data, or say any real data with non-negative support. And now, well, weighted distribution initially, introduced by Professor Rao in the 1965 paper, and it serves as a significant role in the analysis of bias data. For example, in prevalence studies, some individuals have often less chances for belonging to the sample, and this can be regarded as a random deletion of particular values of time to event data. In fact, in our study, we have considered scenarios that biasness could happen due to two specific situations. Either it could be a random deletion of some portion of the population, or it could be due to hidden truncation. Now, when the chances of for these eliminations are proportional to the length of the cases, it becomes a length bias sampling. Now, motivated by this, Pekavedian and Hashemi in 2015, they introduced a mean residual weighted distribution given by this equation, where the mean residual life, MRL function, this conditional expectation, has been taken as the weight function, and the expected value of this mean residual life function is known as the cumulative residual entropy of X. Now, we consider this pi1t as pi of t as the weight function to incorporate the bias involved in the observed sample. The resulting weighted distribution is termed as the stop loss weighted distribution, in short SLWD. Now, we, based on our simulation study and the real data application, this is what we were able to sort of conjecture or establish, that a seemingly imminent advantage for the stop loss weight over the MRL, mean residual life weight, is that the stop loss weight form introduces the weight as the mean of the residual life x minus t beyond the threshold t, without parent truncating the parent distribution, whereas the mean residual life, that weight induces the weight from the truncated distribution. And we claim also that when the investigator is more interested in analyzing a data which is biased due to some random truncation, the stop loss weight will be more appropriate than the MRL weight. But again, we are still working on it to come up with a more real data application, uh, preferably from the financial domain, but we haven't been successful as of now. So there are a couple of interesting lemmas and definition. So if is an absolutely continuous distribution function with a non-negative random variable with a finite mean and the Gini index, which is again a measure of income inequality, then expected value pi of x is equal to mu times g of x. This, the proof is in the paper. And using this lemma, the SLWD, stop loss weighted distribution, is defined in equation point 5. So it involves the corresponding stop loss moment and the Gini index, and the new defined random variable y. If it follows SLWD, will have a form, or it can be constructed by this equation as represented in equation point 5, and it will be known as stop loss weighted distribution. Now, and there are a couple of more other notions. So if f bar tx is given by the ratio, and ft of x respectively denote the survival and the distribution function of the truncated random variable, then the Guinness mean difference of the truncated random variable xt is defined as, and this is due to Nair and his co-authors, is given by in equation point 6. And that helps us to get a closed form expression for the survival function of the stop loss weighted moments, and the form is given in equation point 7. Now, As an example, we started with a Pareto type 2 distribution with location parameter equal to 0. However, I must mention that the usual definition is that the support x bigger than equal to the location. So one could consider as an estimate from the data the smallest order statistics, x bracket 1, and then you could subtract that lowest order point from the data and set equal to 0. So that was the idea. And it doesn't, we do not lose any form of generality. Index of inequality is alpha, and then with this particular form of the density function and the CDF, we were able to find mu of g of x that would look like this, like point equation point 9. And one can easily see that this exists if and only if alpha is bigger than 1. Now, one might challenge us that, okay, how do you know that for a real data set, alpha would be bigger than 1? Well, we, as a usual procedure, we have to collect the data. We can do a test of hypothesis for whether its alpha is significantly bigger than 1 or not. So that's definitely a question. Therefore, now, if we have all this, we also have a closed form expression for the SLWD Pareto type 2 distribution, which is given in equation 0.10. So if a random variable x follows the density in equation 0.10, we can say that x follows SLW Pareto type 2. And one can definitely consider certain other distributions for which you will have finite and closed form expression for the Guinness mean index, and you can subsequently construct the weighted stop loss distribution. Now, in actuarial studies, well, models are often compared by finding bounds for differences in probabilities. Uh, like I said, in most of our intention was to figure out the applicability of this concept in financial arena. So we look at actuarial studies as well as a part of that. So this approach is sometimes questionable when tackling insurance problems, in which the focus should be on the resulting premiums, in particular in the context of our work, stop loss premiums, pi 1t, which is nothing but the expected values of that random variable x minus t plus. This is because small variation in the probabilities of events hardly influence the decision made by an insurance management. And any difference between the calculated premiums, however, will be directly visible. And this is a nice paper by Denuit and his co-authors in 2006, where we got some ideas on this insurance premiums and all related application that we could think of. And based on this, Garber in 1979, he introduced the concept of stop loss distance, which is defined if x1 and x2 are for the two random variables, the stop loss distance is defined as the supremum of their absolute difference between the first order partial moments corresponding to the random variables x1 and x2 respectively, as given in equation 0.11. And then we look at some of the other orderings, stochastic orderings, and also we subsequently developed the stop loss order, which we define in the following definition. So if we have two random variables, x1 and x2, and one can say that x1 is said to precede x2 in the stop loss order, and it could be written as x1 less or equal to SL or suffix x2 if the partial stop loss moment of order 1 for x1 is less than the partial stop loss order moment for x2 for all possible values of t. And we were able to compare the weighted random variables based on the stop loss order. And this is the theorem that we have. So if x1 and x2 upper suffix w be the weighted version of the random variables, then we say that the weighted x1w will precede x2w, the weighted version of order 1, if and only if the corresponding this equation 0.12 uh, holds, where MWIT is the expected value of the weight function given that xi is bigger than t. And of course, uh, the strong assumption that the mean has to be this expected value has to be finite. Now, another weight distribution often useful in situations where the observed data represents a sample that is truncated with respect to some hidden covariates, known as the hidden truncation models, and Arnold and his co-authors have done extensively work on this area, and many literature that we studied during the course of preparation of this paper were very much helpful. However, we look at only one particular form of truncation. It's the lower truncation. So the I mean this is a truncated version that you will observe the random variable or x if and only if y is bigger than some value small y, which is in the support set. So the weighted version of it could be given by equation 0.13. And if you look at, I want to draw your quick attention on the right hand side of equation 0.13. The ratio of these two probabilities, conditional with the unconditional, probability y bigger than small y given x, divided by the survival function of y, that is uh, representing the weight. And what happens that with this lower truncation, you are not augmenting the parent probability model. So in the paper, we looked at this lower truncation form, which doesn't augment the parent distribution. However, if you consider truncation from above, that is, if the weight version is the ratio that probability y less than y, or more general probability that y is between let's say a1 to b1, then the resulting weighted distribution or the hidden truncated version, that will be more general, and that will augment the parent model. So that's another thing that one of the reviewer asked, and we were able to establish that. So and a lot of studies have been made on this weighted density with this particular weight form and several other weight forms. There is a reference by Gupta and Arland in the 2016 paper, and this is like the name hidden truncation model. Now,
You have 7 more minutes.
okay,
In the reel, please. Huh? Okay.
thank you. Yeah. So in the context of lifeline studies, two component system always exhibit the dependence, and there are various notions of bivariate distribution that are used in the literature, and here are some of the references. Now we move on to the bivariate setup. So if x1, x2 be a non-negative bivariate random vector with an absolute continuous survival function, assuming it exists, and Sankaran and Nair, they introduced the R and Sth order bivariate stop loss transform, which is given in equation 0.14. And based on that, Sunoj and Vipin in 2017, they studied the conditional stop loss transform of the form, which deals with the survival function as given in equation 0.15. So based on that, there are several dependent measures that we were able to study. So a bivariate random vector x1, x2 is said to have positive quadrant dependent or negative quadrant dependent property if for all values of t1 and t2. This is the basic definition. And then using the bivariate stop loss transform that was given in the earlier slide, the like a translation of this PQD or NQD notion can be restated in terms of the bivariate stop loss order moments. And we are able to see that this equation 0.16 is equivalent to this particular scenario in 0.17. And if we multiply both sides of equation 0.17 by r times xi minus ti to the power r minus 1 and integrating over the limit ti to infinity, and using the definition of the conditional stop loss transform that was given in equation 0.15, the definition or a revised definition of positive quadrant dependent or NQD will become as given in 0.18, and that holds for all TI. And in the context of actuarial studies, this 0.18, that expression is termed as the positive stop loss dependent. And actuaries intuitively feel that positive correlation between individual risk reveal a more dangerous situation compared to independence. And here are a couple of other definitions that in the process that we were able to mentioned, we are able to establish in the paper. It's about the generalization of the PSLD known as the rth order positive or negative stop loss dependent. And there are a couple of other results that I'm going to briefly mention here. And for example, this theorem, it says that x1, x2 is rth order PSLD or NSLD. Then the weighted version of this bivariate random vector is also rth order PSLD or NSLD if this condition is satisfied. And then we also talked about expectation dependence, and this is from Wright 1987. And it's useful in finance, insurance, and asset pricing. And this is the basic definition. And given in point 20 equation. And then if x1w and x2w is a non-negative bivariate weighted random vector defined on the positive part of the real line, and it is well known that equation 2.1, and based on this we are able to identify the relationship for this weighted distribution with this expectation dependence, and that is given in point 22. And then we also talked about equilibrium models, and Navarro in 2006 defined the bivariate equilibrium distribution. And we were able to identify that the weighted stop loss transform of a bivariate random vector satisfies this relationship as given in the ratio of these two bivariate stop loss moments of order R and S if it follows a bivariate equilibrium distribution defined in equation 0.23. And then we bivariate survival function based on a two non-negative random vector defined in the positive octant. And then this equation, expected value of n1 or xn2 is said to have bivariate equilibrium distribution of order n based on RT1, T2. And it has been obtained as generalization of the bivariate equilibrium distribution to higher orders based on a baseline distribution. And based on that, this is the what we have in the as a theorem. The survival function of the bivariate equilibrium distribution n is given in equation 0.24. So bivariate equilibrium distribution of order n based on the bivariate stop loss transform. So it is given in Gupta in 2007 paper. And that in summary, so what we have done in this paper is that we introduced the idea of stop loss transform. We look at the different weighted version, its relationship with the idea well, biasness or bias sampling could have happened. We look at two different scenarios. Either it could be a random negligence of the some portion of the population, or it could be due to hidden truncation. For the sake of time, I didn't include the simulation and the real life application part, but if any one of you are interested, I'll be more than happy to share the entire paper. So that's what we have done. But yes, there are several challenging factors are there, whether how do you know whether or not truncation has happened and what happens, or how efficient we were able to identify with some developing some empirical estimators in the classical domain, but we haven't touched yet what would happen in the Bayesian paradigm, and what would happen in case we consider more general form of hidden truncation. And these are some of my references that I have. And with that, I will stop my talk. Thank you for your attention. And now I
Thank you. Thank you, Indranil. Thank you very much. You needed much more time. It looks like you had a lot of things to present, but the time is a constraint. Just still, if there's a question, one question we can accommodate. Very quick question. They're already running out of time. Anybody, any question? Quick question? Long question should wait for him. Okay. Any quick question? No, I think there are long questions waiting for you. They'll be mailed to you. Okay. It's a very nice talk. Thanks again, Indranil. So with this talk, our session here comes to an end. I thank all the speakers and all the participants who were here. The initial some hiccups, but finally everything went well. Thanks to Abhishek. And Abhishek, thank you very much for arranging this session. and letting me share this. Thanks to all the speakers. Over to you, Abhishek. We can't hear you, Abhishek. You have to unmute your mic.
Yeah, thank you very much, sir. And it's my great pleasure to say you a big thanks for accepting our invitation. Professor Barry, and then Eric, Indronil, and all of you, and of course, Professor Detrich, who finally